Hello everyone and welcome to the presentation for my project Heuristic Reimagined, an AI approach with advanced heuristics. Everything coded in C++. I am Tanush Gupta and today we will be diving into the world of AI for Othello, exploring search, pruning and heuristics as we examine how to build an intelligent Othello player. So this is for those who are unfamiliar with Othello. Don't worry, I'll wrap it up within a minute. So the game traditionally starts with two black and two white discs placed in the center of an 8x8 board. Our goal is to have the most discs of our color when the board is full or when no more moves are possible. So the core rule is you must sandwich opponent's disc. When you place your disc, it must trap one or more of your opponent's discs between your new disc and one of your existing discs along any straight line, horizontal, vertical or diagonal. Like this, for example, I place my black disc here so that it flips one of the white discs. Now you can see how it has been flipped. So basically this is how the discs are flipped, and the count of my disc got increased by 1 and his disc got decreased by 1, and white also moved in a similar way to reflect the same change. Fine. Each turn player take turns placing this. If I place here, white flips. If white places here, black flips. Fine. For example, like this. Okay. So you can place a disc only where it causes at least one flip. For example, if I try to place my disc here, it won't work because it won't flip any disc of my opponent. So a move is deemed valid only if it flips at least one of the disc of the opponent. And if you don't have any such valid move, then the turn is switched. My turn is skipped and the turn is passed to my opponent. Now if there are no legal moves for any of the players, then the game comes to an end and the board is evaluated, like the discs of both the players are counted and the one with larger number of discs wins the game. So now when we are clear with what the rules of Othello are, let's move it. Again, it's a very simple but a very interesting game. The rules were very simple, but we will see theoretically how difficult it is to take decisions even for such a simple game. Here we are to our code and we would be starting with the project overview from here. So first of all, I've used the CLine ID and it's very useful for such long projects. It helped me along through the hints that were provided by its inbuilt system. And let's start our project overview. So here I would briefly explain what I did in my project and I would give a demo of the system, whole game. So let's start. These were some of the libraries that I used, and I would explain the usage of each one of these in detail. I have used various structures, data structures like classes, structs and enums. There are many more. So there are three major classes in our whole project: the class player, the board class and the game class. And I have used all the things that is included in object-oriented programming, like the access specifiers, the constructors. There was not much need for operator overloading, destructors or anything like the concept of inheritance in this particular project. I could have used them, but to simplify everything and keep the logic simple, I have avoided the usage of such complex things. Then let me briefly explain everything. So the player class is something that takes the characteristic and all. So then the board class holds the positional weights, and this is something which is the home to most of our logical functions. You can see details of each of these functions in the video following. Fine, so I will explain each of these functions in detail. So basically we just implement the logic of creating a hypothetical move by AI and evaluating how that move would fare in future, and we make decisions according to that. Fine, and that code has been implemented in this form. which you are able to see right now. So fine, I will explain each line of this code very well as we proceed. Okay, so one thing which I would like to highlight here is the length of the main function. So my main function was very short, you can see, just because of using all the object oriented techniques. Fine. So now let me give you a demo of how my game looks. See. So first of all, it asks us to whether we want to play against a human or a computer. So I have two options in my game. If I am the player, I could play against another human, which could be my friend or someone like that. Or if I am alone, I can play with the computer. So right now, I would test it with the computer first because this is the most important part of our project. Because here the computer doesn't just play random moves, but we enable it to play strategic moves and it uses such strategy that I don't think anyone could beat it. Fine. It goes much beyond the human intelligence levels. So I would demonstrate the hard AI level, of course. Okay. So here is our board layout. Here is like our board looks like this, the traditional Othello board. The columns are denoted by A, B, C, D, E, F, G, H, the characters, and we denote the rows through from 1 through 8. Okay. And the black player is by default set as the human and white player is set as AI. Now it always first prints the score of the table, like how many white pieces and black pieces are there on the board. Then it displays whose turn it is, and after that it gives us an option to either move. For example, I could move like d3, fine, anything like this, or to ask for a hint from the computer. So first of all, let me show what happens if I enter d3. So first I would check if d3 is a valid move. Of course it is, because this disk would be flipped if I place my black piece here. So let's enter this. I push enter and you see it gets flipped. Fine. So this is implemented in the code. This is something great. And we see the score after the move. Okay. Now computer turns come. Computer is thinking is displayed till the time computer thinks, and we see what computer plays. So C3 has been played by the computer. Fine. And obviously, if you see, if we place a white disk here, this black disk would get flipped. And this is what happened. So till now, everything's fine. Now let's test what happens if we press H. Okay, one thing which I would like to say is we are told to either enter capital H or capital character and 1. So it doesn't really matter if you enter lowercase characters or the uppercase ones, because I have written the code so that it is fully feasible for the user to enter the input in any of the cases. Even if you write like this separated by spaces, then also it would take your input. So there would be no problem. Fine. Even if you put spaces after it, then also there would be just no problem. So I have taken into account all these exceptions which a mischievous user could possibly enter, and these must be handled by a good coder. Okay. So fine. So one thing. So the major thing was we had to test what happens when we enter H. So basically, after I entered H, AI gave me the suggestion of moving to C4. Fine. So this is the best possible move which AI could think, and it is suggesting that to me. And it's my turn again. So let us follow what AI says, because AI's brain is obviously much bigger than mine. In context of this game, at least. Fine. So AI made its move and it's our turn again. Let's now try to enter something randomly. For example, first let's try what happens if I enter D4. Our piece is already placed here and it should ideally display something like invalid or something like that, but it should not place my disk here again. So let's try to enter D4 and see what happens next. So yes, we succeeded. An invalid move is printed and we are told to try again. So fine. So our program was able to check if the disk was already there. Let us try one more exceptional case. That is, we enter something like H6. Obviously, this is also an invalid move because no disk of my opponent is flipped. So let's try H6. Again, it shows invalid move, as it should obviously. So fine, I don't think there are any exceptions left that have to be taken into account. If there are some bugs left, please, you are welcome to report that in the comment section. I am always welcome to feedback and to improve my program. So fine, let me play this game because it's going to be interesting, I think. I hope to be beaten by the AI designed by me because I want it to be better than me, of course. So let's see what happens. I'll fast forward this video so that you can see the result. Okay, so I played a whole game with my AI and this was the first game I had played. So yes, I believe that I am a decent Othello player, but AI had beaten me very nicely. Though in between I lost confidence in the code when the score was something like 16-6. I was with scoring 16 pieces and the AI was just at 6. So I thought that there was a bug in the code or something else, the algorithm wasn't functioning. But still, I was much relieved with the final result of 1252. Basically, this is because normal human ideology, like we only can imagine till one move. We only think about the parity of moves, the count of disk at any moment of time. But I have enabled my AI to think in many dimensions that would be disclosed in the video following video. So this is a must watch for you. And okay, I've attached this whole game as a PDF for you if you want to see, analyze how it went. And I also took several hints between the game, but I wasn't still able to beat with my AI. You can also try playing with it. I will attach the code also if possible. So see, okay, I would like to unshow the algorithm, the face of those functions that actually enabled the AI. So these are basically the 3 or 4 functions: the max value function, the find best move function, this min value function, and here the evaluate board function. So only these 4 functions are composed of the whole algorithm. Rest all the lines of code are just for orchestrating the game flow and either to help these functions to run or to keep them running in a loop or something like that. So we would be focusing more on this part, and for that we would need to learn some theory also, and all of it would be included in this one video. So what's the fundamental goal of the project, the Othello engine? Primarily, it's to develop a complete and robust digital version of the classic Othello game in C++. But the real heart of this project and the central challenge we set out to tackle was, how do we design an intelligent computer opponent? So how can we make a machine make strategic move instead of just flipping random disks and thinking randomly? This is not just only a game, but this paves way to the further concepts in artificial intelligence and algorithmic thinking. This challenge of decision making in a competitive game-based environment is exactly what paves the way for us to dive into vast and fascinating field of artificial intelligence. To build our intelligent Othello player, we naturally encounter and implement several sophisticated AI concepts. Throughout this presentation, we'll explore key ideas like search algorithms, how a computer can systematically look ahead to find the best moves. We'll also have an introduction of game theory, the mathematical framework for understanding strategic heuristics. The heuristics, the keyword, is the practical rule of thumb that computers use to evaluate the board and complex situations quickly. So our overall aim is not just to build a game, but to use Othello as a powerful case study to understand and apply these fundamental AI principles for strategic games within our Othello engine. And besides, we'll also learn a lot of syntax and coding concepts in C++. So to gather enough motivation before starting our project, let's look at the learning objectives. First, we'll continue our under the hood exploration, but this time it's about the very core of our project, the detailed line-by-line code walkthrough in C++. This is where we truly understand how everything fits together, from fundamental board logic and how players interact with the game to deeper complexities of AI implementation. We will also specifically justify the design of our AI heuristics, especially that positional weights table that we glanced, and why certain values are chosen, etc. Then by the end of the session, my goal is for you to walk away with a clear understanding of several key areas. Firstly, how classic board game like Othello can be successfully digitally implemented as a robust engine. This goes beyond just playing into building a modular and scalable system. Secondly, you will grasp the fundamental of AI decision making in games. We will see how algorithms can make intelligent and strategic choices. Thirdly, you will understand the power of Minimax algorithm and its enhancement known as alpha-beta pruning. And finally, this project serves as a fantastic case study for practical C++ object-oriented programming applied to the game development. You will see how classes, structs, and various C++ features come together to build a complex system. So get ready for a deep dive into both AI theory and its practical implementations in C++. So now you have seen how the game works and everything about it. So now there's a question for you. Can you guess the best move for white? No, it's not a very easy question as you might be thinking right now. And it involves complex mathematical calculations. Not exactly calculation, but various such algorithms. Okay, fine. So let us spare a minute for this. You might think that we should place our piece here or here, as it would flip the maximum number of pieces 3 on the board. But we would soon figure out that this could be one of the worst possible moves. How do we find the best possible move? There were about 2 to the power of 60 possibilities from that particular position till the end game. So it wasn't possible even for the computer to go through each of the possibilities and check which one would be the most favorable one. And I did try to calculate the time it would take for an average computer, which came out to be about 76 years. So if you are ready to spend your whole life to calculate an Othello move, then you are most welcome. Okay, jokes apart, we should start our logic. I would try to explain some search algorithms in AI. Okay, before starting that, we should learn what a decision tree is. So let's analyze this figure to understand what a real decision tree is in our Othello game. So this is an hypothetical figure. Say this is an situation on the board at a particular time in the game. So imagine you have two moves to make. You have an option of making either this move or this one, and the board could be placed like this or this when you make either of the moves. We will analyze which move is the best by traversing through this tree. For example, you make this move, then the board would be like this, then the opponent would have these moves possible, and the board could look like this. and then it would be our turn again, and the tree could be extended till whatever depth you want. Same here, you could analyze this branch also, and here also the board was like this, then the opponent has two options, then you might also have further options. So it's like this. Now we consider these boards as nodes. These are nothing but the state of the environment which we are currently in. These are referred to as nodes. The branches are nothing but the choices which we are making, the available choices which we have. And the resulting state of the board is known as children of the root node or the parent node. Look through each of its components right now. These circles that you can see are nodes. These are known as edges or branches, and the terminal nodes. The nodes which don't have any children, we call these generals the nodes that emerge from the parent node are known as children nodes. So, and the terminal nodes are known as the leaves. The node which starts the whole tree is known as the root node. Basically, this is a graph. A graph is collection of nodes and edges, and tree is just a case of graph. Okay. So what our aim would be to search through. For example, you have various values on this trees written on this tree written down, and you have to search for a particular value. Then you would start from here, then go here, here, here. This tree could be infinite or whatever. We will look through how to search for a particular node in this tree. For serving this purpose, we need to know various search algorithms. There are two types of algorithms we have in our theory of game AI, that are informed and uninformed search methods. The uninformed algorithms do not use heuristics or other things. So let's explore them first because they are simpler. There are majorly 3 to 4 types of uninformed search algorithms, which is BFS, DFS, and UCS. And let me explain first two of these to enhance your understanding. DFS. So here comes our decision tree. DFS is simply depth first search. As its name suggests, we first search till a particular depth. Maybe till full also. We can set the depth and it is known as IDDFS, iterative deepening depth first search. But here we look into the depth first search only. You can look through IDDFS if you want to. I'm not covering that right now because it's not very relevant. Now DFS basically, what DFS basically does is it would first try to find the node till a depth. For example, it would first check if this is the target. If it's not, then it will check this one. And if this is not, then this one, then next, and so on. And if if the depth gets exhausted, the tree gets exhausted, we reach to a terminal node, then it would go back, and that is known as backtracking, used in various games such as maze solving, these things. Then it would go through the another branch and search the whole depth. Same here also. So yeah, the breadth first search first traverses the breadth of the tree. The depth is basically, it makes me. So we call this as the breadth of the tree, and this as the depth, you can say. So the depth is like this, and the breadth of the tree would be like this. So we saw that DFS first traverses through the depth, and BFS would traverse the breadth first. For example, it was first investigate that if this is the target node. If it's not, then it would through a for loop or any other thing, investigate if these two are. Like it might first investigate this one, then this one. And if these two are also not found to be the target nodes, then it would go through 4 of these. It works like this. So these were the uninformed strategies, and now we come to the informed ones. Before going ahead, we should know what a heuristic is because I might be using this word apparently and you might be confused. So a heuristic, as Wikipedia defines it, is any approach to problem solving that applies a pragmatic method that is not fully optimized, perfected, or rationalized, but is nevertheless good enough as an approximation or attribute substitution. So basically, it is nothing like we are not searching till the whole depth, as I explained to you earlier. Also, we can't search because it would take a lot of time. So it is basically a shortcut, you can say, but we can usually rely on it till certain depths to give us the best possible result. And we don't have any other better option. So yes. Now informed search algorithms include things like greedy BFS. Okay, we might skip this for now, even if I want to explain it. Okay. So greedy BFS is nothing but it would first, before going to the nodes, it would first explore them. Say, if we have scores allotted to these nodes, it would search to all of these, and the best of these, the scores, would be taken. A star search algorithm would be one thing which I would try to focus on. This is something that relates to my project of making the Othello agent intelligent. We have already, okay, we know what decision trees are already. Okay, so let's study a little about A star search algorithm at it as it might be used. So there are three components of A star search algorithm, that is heuristic function that we denote as h of n. N is the number of nodes that we have traversed till now. The cost function is usually denoted by g of n, and it is the number of nodes we have already traversed till now. And this is the evaluation function that we might use in several cases. This basically assigns a weight w1 and w2 to gn and h of n. We won't be using just g and h of n in our project because it is not simply a graph search algorithm and we don't have any such target node, but we have to compare several nodes and choose the best among them. So basically, yes, our heuristic, overall heuristic would be something like a combination of many heuristics. Like I might find one thing like this parity of the board. Parity of the board means my pieces, black pieces minus white pieces, as I'm the black player always. So parity, and there might be other factors too like mobility, so and many others too, and we will assign specific weights to them that change during the gameplay also, and we will look into it further. Moving on to a crucial theoretical concept that underpins our AI, game theory. You might be thinking that game theory is nothing but something that just manages the game, analyzes the game, and it is nothing related to anything else. But no, it's not true. Game theory is a very vast field of mathematics that deals with fields related to finance, economics, and even artificial intelligence that we would be exploring through this project. As the slide states, game theory is essentially a mathematical framework for exploring how rational players make decisions. It basically analyzes their choices and strategies, always in the context of competitive situations, and how those choices lead to different payoffs or outcomes. Let's quickly break down the key elements that game theory considers. So as you can see, there are three of them: players, strategies, and payoffs. Players are the decision makers, the doers of our game. Here in our context, there are two players. One is human and the other one is possibly AI. Strategies are the possible choices and plans of action available to the players. For Othello, a strategy isn't just one move, but a whole plan of how to play the game, influencing their potential payoffs. Payoffs are nothing but the outcomes or results of a player's chosen strategy. In Othello, payoff is directly tied to the final discount, who ends up with more discs. It reflects their success in the game. But as we move forward, we would see that we would define payoff in a different way using weight analysis and heuristics. Now there are some basic game theory concepts that we need to go through briefly. What's particularly relevant for Othello and for many competitive board games is the concept of a zero-sum game. So we should understand this very well. Zero-sum game is a sort of game in which when one player gains, the other player loses. There is no such scenario where both the players win or lose simultaneously. The total value of the game's outcome must always come zero. So this is the one which leads the Minimax algorithm to work. Now one important question is that you might think that every game is a zero-sum game because whenever one player gains, the other has to lose. But no, it's not true. You could explore the exceptions like prisoner's dilemma, and these work through Nash equilibrium. There is a situation called Nash equilibrium which I'm not exploring right now, but because it's not very relevant and it would go out of scope of my project. But basically, Nash equilibrium is nothing but a situation where all the players are in equilibrium of choices. No one has any regrets and all are winning or all are losing. Basically, there is no win or lose there because all are in total equilibrium. We will see these having applications even in real life, like economic negotiations, as I told. Let's move ahead. I think you already got an idea of what payoffs are. So now we come to the Othello decision tree. I explained this already through the previous slide, and we come to this again because now we will be starting our algorithm part, and now you should gear up to see some code and the pseudocode logic. So let's briefly check this out also. What we have is a max player and min player. This might be something new to you. So we are defining something like score. Score is basically my score. The value of a node is my score minus operand score. Now you might wonder what this score is. We will see how we calculate the score from the position of a board by applying heuristics and other things. So need not worry about this for now. Just think of it as the value of a particular node. Okay. Now what a max player means? Max player is our AI. I would be explaining every slide from the perspective of AI only because I am just optimizing the decision of AI. The human is not in my control. So the max player is AI. For example, if I am playing, I would play to maximize the score. The score is my score minus operand, so sorry, maximize the value of the node, this node. And the other player would definitely try to minimize the value. So Othello is essentially a zero-sum game. Whenever my score increases, the opponent score obviously decreases. Okay. So you got what a max and min player is. We can move ahead. Now this is the pseudocode for our Minimax algorithm, and let me explain it through an illustration, and then we'll go back to the pseudocode to investigate how it works. Firstly, if you were to okay, let's say this is an hypothetical game situation and you have to choose between these two moves. Here AI is standing on a board at a particular time and it has to choose between these two moves. The value of these is not currently determined. We will see why is this so. Suppose it chooses this one, then the opponent has two choices. either to choose this node or this node. Now opponent evaluates the board and says that if I choose this one, then the score of me, AI score would be 2, and if I choose this, AI score would be 6. You can see again that opponent is the minimizing player. He is working to minimize the score of minimize my score. My score means AI score. So he will definitely choose this 2. So this comes out to be 2. The value of this comes out to be 2 because he chooses the minimum of these. Okay. Now going again, if I choose this move, then my opponent would have two options of choosing either this or this one. Now again, through the same logic of minimizing player, he would choose this one, this node, because this has the minimum value. So this node would get a value of 1. I think this should be pretty much clear. Okay, you might be wondering that why does not this have rest children nodes? It could have, but this is just for a simplified example to illustrate the working of algorithm. Okay, so now we have the values of these nodes, and it is now AI's turn to choose among these. Now the AI is working to maximize the score. So he would the AI would definitely choose this node, and the value here would come out to be 2, which is the final result. Okay. So basically we also got the path through which the game proceeds, which was this one. Now it is so simple to visualize like this, and we can say like we sometimes think that we can think like this till as much depth as we want. But it was not so easy to explain even when I explained it only till depth 2. When we have to think like till depth 6, 7 or 8, like it goes out of the bounds of human mind and intelligence. So we need specialized algorithms to do this. Now we see the algorithm that perform this task for us. Okay. Every algorithm that I explained would be in form of pseudocodes only. They are not in any particular language so that they can be implemented anywhere. But I will try to explain everything. So you not to worry if you are not very familiar with pseudocodes. I'll take care of that. Okay, so we define a function max value. For setting up our minimax algorithm, we first need to understand about these two functions, max value function and the min value function, and then we'll proceed to the final max. The max value function is nothing but it just mimics the maximizing player. It does exactly what the maximizing player has to. And same for min value, it is just a representative for a minimizing player. Okay, so let me first explain the max value. If terminal S, okay, what is S? S is an argument of the function and it is the node which is being currently passed. For example, here I would pass this node. Say if this node is called as S, then I would pass this node into the function. This is just a pseudocode. Don't worry about how will I pass a node to the function. Like node is not very much defined right now. But don't worry about this. We will see it in the implementation part, how to do this. Okay, so max value S. I pass the node and it evaluates the node basically. Okay, if first it checks if the node is terminal or not. If it's terminal, then it returns eval s. Okay, eval is another function that is used to evaluate the node. How this is implemented, again we will see when I go to the code. Right now we are just understanding the algorithm. Every time the process of critical thinking goes like understanding the algorithm first and then implementing it. So let's first understand and then implement. It just returns the eval s returns the value of s. Here it is 2, but okay, it won't work here because the node we selected is not terminal. Okay. we declare a variable v equals to minus infinity. Okay, we'll see why. For c in children s. Now this line does nothing but expand the node. Now it will create all the children of s. The children of s here were, let me label the nodes a and b. Say we call this node as a and this as b. So the children of s were a and b. For c in children s, c is another node. V dash equals min value c. Okay, here's the most tricky part of this algorithm. We are using another function as a recursion in one function. So min value c would do nothing but choose the minimum of the children nodes of this a node, c node in our case. For example, we are passing c through this min value function. So it would return the minimum value that could be obtained through the expansion of c and the rest of the decision tree ahead of it. So v dash equals to min value c. This is another variable v dash. If v dash is more than v equals to v dash. Okay, now let me explain it again. So basically the min function chooses the minimum value that it could obtain from the tree below this node, and it sets the value of this node as that value, the minimum value. Now we had an initial variable v equals to minus infinity, and we check if the value which we get right now is more than v. The value which we got right now was labeled as v dash in our pseudocode, and we check if the value v dash is more than v, then v is set as v dash. So if v dash is more than v, then we say then v would be set as v dash. Fine. So why do we do this? V is nothing but the maximum value that we could get as from the perspective of max player. I think you would get the logic. It's pretty much intuitive, very intuitive. So we set v as v dash, and again this was just one children. It would go again to b to produce the other children. V would certainly expand through the min value function, and it would yield the value of 1, the minimum value. Here after this our v was updated to be 2. Now if it again, this is v dash for the second child, it again checks if v dash is more than v, which comes out to be false in this case. So it won't update v, and the final v would be 2 only. Okay. Now we return v. We return this value 2 here, and we get the maximum. So yes, this algorithm totally works, and the min value is very similar to max value. The changes are just plus infinity, which you can get, I think, and the max value function obviously, and here the inequality of changes. This is again runs through a similar loop as the max value. I don't think I need to explain this right now, because we have got sufficient understanding of the max value, and you can decipher the logic of min value from its pseudocode. It's pretty much intuitive once again. Okay. So now we take a stride and go to the Minimax algorithm. Now the Minimax algorithm is pretty simple after you have understood the max value and min value functions very well. It just groups both the functions into one and does nothing else. So it's very simple, and let me tell you that I'm not writing the code for concisement. Like during implementation part, we would keep these functions separated. It obviously it makes the code easier to debug if we keep the functions separated. It is called modular programming. And I would not group these into a minimax loop, but I would explain for your understanding. So there is a function called minimax, and it takes the parameter s, d, and max. So s you are already familiar with, it's just the starting node, and d and max are the two new arguments that you need to see what they are. D is nothing but the maximum depth till which the algorithm will search. Say if this tree would not have terminated here, it would have gone maybe till infinity, or I don't know till which depth it will go. But this is very dangerous for the memory of the computer. Like we would not be able to calculate a single move if we would not specify the depth. If we specify the depth, it would just limit till a particular depth. For example, if I say d equals to only 1 here in Minimax, so it would search only till here and nothing else. It would do nothing else. Okay, so d is the maximum depth till which we search. Max is a boolean variable which just checks if we are the maximizing player right now or the minimizing player right now. It could be a bit confusing right now, but don't worry, we'll see as I explain the pseudocode. If terminal s or d is more than max d. So again the same condition of terminal s that I explained. If the node is terminal, it returns eval s. We discussed about this function already. And here's a new condition, d more than max d. So remember what we said d was. D was nothing but the maximum depth till which our algorithm is searched. So if the depth is more than that max depth, if it's more than that max depth, it would terminate the whole algorithm and return this s. We don't want to go beyond this max d. Okay. If max. So if max is nothing but, this says that if max is not equal to 0, max is a boolean. So 0 means true. Sorry. 0 means false and 1 means true. So if this is true, I am the maximizing player. It executes the code for the max value function. Exactly the same thing. And this is nothing but a simplification of that if else statement that we saw in a max value function. It would run minimax, again would see d plus 1 and false. False would be just for like if I am already the maximizing player, the next move would definitely be made by minimizing player. So I am initializing the variable max as false because the next move is to be made by the minimizing player. Okay. D plus 1 because I am already searched till depth d, and it will now start the search from a depth of d plus 1. And C is the S, our new S, the child of max. Sorry, the child of S right now. Okay. Now, if I am not the maximizing player, I am the minimizing player. And here's the code for the min value function in just written in another form. And similarly, you can see that this is the simplification for the if else statement, the min. This is the node. Like this is the minimum value that we are getting right now. And it would compare this one and this value. This value again comes from the max value function. Max value function is this snippet of the code. Again, to explain these arguments, we have C is just a children of S. D is again because we have already searched till depth D, and true is because if I am the minimizing player, the next move would be made by maximizing player for sure, and the max variable would be true. Okay, so now I think the Minimax algorithm should be pretty much clear. and we have more than half of our work done, and we are just left with the enhancement, but that's the most important part. This enhancement enables us to cut out most of our work, and it would make our algorithm very fast. So first let me explain it through the illustration how we will prune the tree. So our enhancement is called as alpha beta pruning. Why it is called pruning? Basically, we will be cutting out few branches, and that is what the essence of pruning is, removing the dead branches or the unneeded ones. Okay, let's simulate the process of decision making once again, like we earlier did. We are the maximizing player, which we call AI in our context. So let us start from here. I have two choices, this one and this one. If I go to here, I already discussed that it would choose between 2 or 6. The minimizing player would choose between 2 or 6 and would yield 2 here. Going to this node, we come first here and we see a 1 here. Okay. So now can I say that this is minimizing player? So the value of this node is going to be less than or equal to 1 every time, no matter what this node is. See, I have expanded till only this node right now. I have expanded only till this node right now, and I don't know what this is. But for sure, can I say that this would be less than or equal to 1? Okay, this might not be very intuitive. Say we have a value more than 1 here. This is the node which we haven't explored till now. Okay, ignore this value of 8. We haven't explored it right now, so we don't know what it is. Say it is something more than 1. The minimizing player would choose between 1 and something more than 1, the minimum of them. So it would choose 1. Fine. And say if it is something less than 1, then it would choose this value. Again, because this is the minimum of 1 and this value. So in every case, the value which we attain at this node is going to be less than or equal to 1. Okay. So now the work is too easy. We will apply the same logic again for the max player. The max player has a 2 here and something which is less than or equal to 1 here, and it has to choose the maximum of these variables. So now can you think what the value of this node? We don't know what the value of this node is, but still we can guess the value of this node. So I think you all would have got it already. This would be 2, because maximum of 2 and anything less or anything which is less than 1 would be 2 only. So this was just like magic. We did not have to expand this node at all. We didn't even have to find the value for this node. Like right now it would seem like there was not much of simplification. We just cut out one node. But imagine if this node was running till a lot of nodes. This was being expanded a lot. This was the one who was the main criminal in the sense that there is a node which slows down our program. So it sometimes saves millions and millions of seconds. Okay, so we can cut this branch totally from here and from here. First we cut this branch at the minimizing clears node, and at the maximizing clears node we cut this branch. So our tree is essentially composed of just this part, and this is called the pruning. Okay, I think you have got the logic very well, and let's go to the pseudocode now. Okay, the pseudocode is not very different from the max value and the min value functions, which we have already understood very nicely. to reflect the differences, I would run these in parallel. Can you spot out the differences? Okay. So the differences are these three arguments are added to the max value function, the traditional max value function. Also, you see that there are there are two new lines of code added. There were initially 8 and now there are 10. So we don't have to care about the rest part. Rest part is just same as the max value which I initially explained. And here D is also nothing but I explained the maximum depth thing. So it also need not be explained right now. We have to focus just on these variables alpha and beta, which also give the name to the algorithm alpha beta pruning. Okay. So let's set out to tackle this challenge, how alpha and beta work. You can visualize alpha as the best guaranteed something that the maximizing player is guaranteed to achieve. For example, here the maximizing player was guaranteed to achieve some value of greater than equal to 2. So after we got through this loop of this node, our alpha was 2. Because after we got a value of 2 here, we know that this node is going to be more than or equal to 2. Fine. So alpha is 2 here because it is the guaranteed value, minimum guaranteed value that the maximizing player would achieve. And beta is just symmetrical counterpart of alpha, and it is the minimum guaranteed minimum guaranteed value that minimizing player would achieve. For example, say when we expanded till this node, we already knew that this is going to be less than or equal to 1. To enhance our understanding of the functioning of the algorithm, let's go through the pseudocode once and through the decision tree simultaneously, so that we know what line of the pseudocode executes what in our decision tree actually. Fine. Another thing, I am hiding my video for some time as it was blocking the view, so that shouldn't be an issue. Okay, so let's run through this algorithm and mark several things on our decision tree. First of all, we start with this node and we pass this node into the function as S. Also, as this slide states, we initialize alpha as minus infinity, beta as plus infinity, and D as 0 right now. So here, while executing the function, D refers to the depth that we have already explored. So at the start of the function, we have explored till depth 0, obviously. Fine. So now, this is the initial state of our game, and we are the maximizing player, so we pass the initial state from the max value function. Fine. Okay. So if terminal S or D equals max D, for now I am assuming the value of max D, which is obviously a constant, as 3, because my tree on the screen is still a depth of 2 only. Okay, so max D is 2, not 3, sorry. Fine, so if S is terminal or if D is more than max D, then return eval S. So this condition is not satisfied as neither S is or terminal node or neither D is more than max D. So we move ahead and we initialize a variable V as minus infinity. Now for C in children C, children S. Children S is the subset, a set basically composing of these two nodes A and B. Okay. V dash equals min value, C alpha beta and D plus 1. So we recursively find the values for these through the min value function. Okay, so let's first go to this children C1, which is A, and let's apply min value algorithm to it and see what happens. Okay, so from this line, I go to here. Again, this is skipped and this V. Okay, so this V and this V are different. It's just a pseudocode. So try to understand. These are different. So I initialize this as plus infinity and I again expand this node through its children and let's see what happens. So, okay, for C in children X, V equals max value C alpha beta D plus 1. For now, my child C is this node. Let's label this as C. So C is this node and this would be passed through the max value function. But as S is terminal this time, when we pass S as this C, this would come true, this statement, and it would just return the value of S. So V dash would become 2 here. V dash would become 2 here for the first time. Okay. Now let's move ahead. If V dash is less than V, which it obviously is, V would become V dash. So V equals to 2 from here. Now we see what we have next. If V dash is less than equal to alpha, then return V. Okay, so our alpha was minus infinity and this statement is not true. So we skip this. If V dash is less than beta, then beta equals to V dash. Beta was plus infinity. Fine. And V dash, that is 2 is less than infinity. So beta becomes 2. Okay, so here our algorithm actually returns a good thing for us. Beta equals to 2. So do you remember what beta was? Beta was the guaranteed value, the maximum guaranteed value which the minimizing player would attain. And here it is 2. As we got to this node earlier also, I told you that after we have attained a value of 2 from this node, we know that we would get a maximum of 2 at this node. And this is what beta represents. Fine. Okay, as we move ahead, this node 6 is again, this node is passed. Again, this becomes the C, my child right now. So this node is again passed through this max value function and its value is returned because it is also a terminal node. But this time the value of V dash would be 6. Fine. This time the value of V dash would be 6. And when we compare it with the value of V, it comes out to be larger than that. So the value of V won't be affected. See, this statement won't be executed. Okay. Again, alpha is minus infinity. This statement is also skipped. And if V dash is less than beta, no, V dash is not less than beta. This one is also skipped. So the value of this node is 2 because it finally returns V and our V was 2 as you can see. Fine. So we get a value of 2 from this node and recall from where we started. This we were aiming to get the value for this variable V dash in this max value function. So here V dash is assigned a value of 2. V dash is assigned a value of 2 and exactly as the min value function it would be compared with the value of V and V here was minus infinity. So obviously this statement would come true and would be executed. So V would be set as 2. This was V dash and V would also be set as 2 right now. Okay. And we see the most important thing here again. Okay, this statement wouldn't be executed because beta was plus infinity and v dash is obviously less than that. Okay, so the most important thing in this max value function is this statement again. V dash is more than alpha, which it is right now because alpha was initialized as minus infinity. So alpha is set as V dash, which is 2. Again, see what alpha was defined as. Alpha was defined as the minimum value which the maximizing player is guaranteed to achieve. And it is so here also. Because after we got the value of this node, it was confirmed that we can get a value of 2 even if it doesn't matter what the value of this node is. So alpha should have been set as 2 actually also, and it is working. So our algorithm is working till now. See if the algorithm continues to work from here on. So after we have passed one children a from this min value, we were actually running through this loop and C was first labeled as A, and now it's B's turn. So B would be passed through this min value function. In the min value function, these statements obviously come wrong. V is set as plus infinity once again, and we analyze the children of B. So we first go to this and then to this. So first of all, we are here at this node, and this is set as C. Okay, so first we need to determine the value of V dash, and for that it is passed through this max value function, and the max value function stops at this line only when it sees that this is the terminal node. So V dash is given the value of 1. And we had set V as plus infinity, and when we compare V dash and V, we get V equals to V dash. So V is also set as 1, same as V dash. Okay. Now we compare what now we come to this statement and see if V dash is less than alpha. Let's see. Our V dash is 1 and alpha is equal to 2. So what do you think? This is true, right? So it directly returns V. And what was V? V was the value of this node. Sorry, this is 1, 1. Really sorry. So V was the value of this node, and it had to be determined through comparison of these. So basically how this works is, if this has to be less than or equal to 1, fine, it had to be more than sign here. I'm sorry, okay, so this has to be less than or equal to 1 here, and it has to be 2 here because this can't be 2 in its maximizing strength. Fine. So even if we assign a value of 1 here, which might be wrong actually, because this could be even be less than 1, like 0 or something, but the value of this node won't change. Value of this node won't change by this node because we have already got a value which is less than alpha. So we can ignore what all is contained, what information is contained in this node. So we just prune this branch and we don't have to look into it. Fine. So this is how the pruning works, and this V here is set as 1. Again, when it has determined the value, it would run these statements again, and these would come false because here V dash is not more than V, because this would be set as V dash for the max value function, and our V was 2 here. For this particular node, our V was 2 and V dash would be set as 1. So V dash would not be more than 2, so the value of V remains unaltered. Also, these statements have no effect now as the pruning has already been done, and V dash is obviously not more than beta. Neither V dash is more than alpha. So neither of these statements is executed, and finally we return the value of V as the value of our node, and the algorithm comes to an end. and we have determined the value of node without calculating what there was at this node. So this is what alpha beta algorithm uh, establishes. Basically, you might see that this didn't reduce our work much, but again, I think I explained this earlier also. This node could be something which would make our workload too much. So basically, we save the time needed to compute this branch. Okay. Now let's go and implement this algorithm in C++, and before that we'll see how some functions in our project have been defined which help us to write the code for minimax and alpha beta pruning algorithms. There's an option to directly jump to the implementation by using the timestamps I have provided. So if you would like to see the implementation directly after the logic being explained, so you can go through that path also. Fine.
Okay, so before we dive into the specific code, let's take a step back and look at the overall architecture of our Othello engine. This is crucial for understanding how the different pieces of our C++ project fit together and communicate. Think of this as the blueprint for our application. At a high level, our project is designed around three primary classes, each with distinct responsibilities. The board class. This is the heart of our brain. It encapsulates everything related to physical board itself. It manages the 8x8 grid of disks, knows the rules for valid moves, handles placing disks, and other things like this. It also contains the AI's logic, including heuristic evaluation function and the minimax and alpha beta pruning algorithms. Essentially, the board class knows how the game is played and how to think about playing it strategically. The second comes the player class. This class represents a participant in the game. It stores essential information about each player, their name, that is either black and white here, whether they are human or AI, a very important aspect, and for AI players, their difficulty level also. It's a data container that helps us differentiate and manage various players in the game. The game class is the orchestrator or the conductor of entire application. It handles everything related to input and output, and its primary role is to manage the flow of the game. Like it sets up the game, handles turns, prompts the human to give input, and it also instructs the AI to make moves and other things like this. So it essentially ties all other components together to create a runnable game experience. Now we'll dive into the specific code now. Let's start. Here you can see another slide which mentions all the variables and functions which are encapsulated within all these classes. So from these two slides, you can get a picture of whole project, and this slide explains everything, the functions through arrows and symbols. Now, this is the start of my code. Like any other, it includes a lot of libraries, and I'm not going to explain it right now, the function of each and every library right now, but I'll explain its usage when in future they come into the application of our program. For now, we use the IO stream, that is input output stream in the whole program. It is basically nothing but a library which is used to take input and output from the user. Okay, using namespace std is a standard command which just avoids to use std before every iostream command. For example, we won't have to write std : cout. We can just write cout for displaying the output to the screen. Now here are two new data structures that are enum class and struct. So enum class is a custom data type with a fixed set of named values. So the variable of this class, enum class, can assume between these three values, empty, black and white. And I have used the variable name as child state. So essentially state of can only be either empty, black and white. So this makes the code highly readable. Struct move. Structure is a simple container that groups related variables together, and here I have used it to club row and column. Basically this just represents the position of a disk on the board, and we know that we can distinctly represent any position on the board by two parameters, that is row and column. Okay, so we start with our first class, the player class. And here we are introduced to the concepts of data encapsulation. Like we use the keywords such as private and public to encapsulate and use it for data hiding purposes. This basically improves data integrity and reduces accidents. For example, I could alter some data which I should not alter, and if it is stored within a class as a private member, it won't be altered anywhere else in the program. So as now investigating about the function of this class, we can see that it just stores the characteristics of a player. For example, name, symbol, and level, etc. It also has some functions which are used to get these variables from the user or from elsewhere. One important thing here we see is this function. It looks quite weird because, okay, firstly the name of the function is the name of the class itself. The second weird thing is the braces, which usually contain the definition of a function, definition of a traditional function, are empty. And there's a colon and some list, like it's quite unusual. This is something we call as a constructor, class constructor. It has the same name as the class, and this list is called as the initialization list. It basically helps us to concise the code into one object. For example, I could instead of this just write that name equals to n, symbol equals to s, human equals to human, and etc. within these braces. But this list makes it quite clear about what my intention is. Okay, so yes, you can, I think the default arguments mentioned here should be quite clear. The one thing which I would like to mention is the default arguments are always mentioned on the right hand side of the left arguments. Fine, so they are always towards the end. Like I would not write bool human equals to true and then still state s after it without specifying its default value. This is some nuance of C++ syntax only. And we also use the word const before many functions here. So this guarantees that the function will not modify any of the object's member variables. This is just to get the variable but not modify it. Okay, so we can move ahead. Now here starts the most important part of our program, and this could be an exhaustive one because the board class is the largest class containing all the logic and the most important functions of our project. Okay, so first of all, I have already mentioned about the private and the public access specifiers. Here we use a variable called size. Constant size constitutes because in our program the size is constant and that is 8. I could have kept the size variable also. I did try, but it would just unnecessarily make the project complex, so I decided to keep the size constant as 8 for now. We can update it in the future, but the innate flexibility of the whole project is like restored just because this is not just taken as 8 but a variable size, so you could maybe alter it later if you want to. For now it's constant. Okay, here a new data structure, vector cell state. So this is nothing but an nested vector. First let's understand what a vector is. I think you would all know what an array is. So a vector is nothing but a dynamic array. We know that array is a static variable, static data type. Like its size cannot be changed. The main thing is this, its size cannot be changed. We can access its element and we can change the elements, but we cannot change the size arbitrarily. Like if an array of size 8 has been defined, you can't add a ninth element into it. So the solution to this problem is given by this data type called as vector, which is known as a dynamic array. You can delete elements from this vector and you can even add to them. Okay, the addition we usually do by using the pushback function, which adds an element to the last of an array, and the popback function is used to pop the last element, like delete the last element. So this essentially functions like a stack, if you know the stack and the queue. So this functions like a stack, but it is not exactly a stack because we can access all the elements, all the positions, which we cannot in stack. But the pop in and the pop back functions are just like the stack. Okay, so moving ahead, constant positional weights. This is the possibly the most important heuristic part of the function. We specify the positional weights. So what positional weights is, you might be confused. This is basically the scores given to various positions. Like if I place my disk at a corner, I would be given a score of 120. But if I place my disk at this point, my score would be decreased by 40. The overall score of me would be decreased by 40. How we derived this table? Let's see. Okay, so basically this was the theory of this game particularly, and there is not very much justification to these values because it is essentially the theory of this game. But just to explain it, you can get some intuitiveness out of it. Like corners can never be flipped. You cannot flip it through any direction, so obviously the score of the corner should be very high. And also corners can be used to capture these long diagonals and the sides. Like corners can capture a diagonal and two sides if you want. So they are the most important pieces and thus assign a value of 120. Apparently the pieces, the cells next to the corners get a very low value, the lowest one in the whole table, just because it makes it very easy to capture corners if you place your disk here, right? And the center squares, you can call them a bit neutral, like they are not given a very high or a very low score because there is no such thing. And obviously the edges are preferred from the center because the edges help us to capture more pieces and they have less probability of being flipped. So fine. Now we move to the main functions of our board class. There are pretty much of them, so be patient. The first one is check direction. Okay, so check direction functions checks if I can move in a particular direction. I would explain it through this figure, the whole function. We would go into the syntax and the lines, but let me first explain how it functions. For example, let's first explore what the arguments are. The arguments are cell state player. We already defined what a cell state is, the structure. Now the cell state player, row, call, d-row and d-call. Row and call is nothing but the position at which we intend to place our disk, and d-row and d-call are the directional values. They are the directional values. So let me first explain it to you. Okay. So it checks if, like for example, if I say I have this white disk and I have to check what all valid moves, in what all directions I can make moves. So if I say this direction, can I move in this direction? So through some logic, this direction would be okay. Through some logic, it would return a true because I can place my white disk here, and all these blacks would be flipped. And to mention like d row decall to define these, the d row and decall just represents the directions. When d row is positive, it represents we are moving to the right of the board, and when decall is positive like +1, we are moving to the okay, sorry, when d row is positive, we are moving towards down, like this is the row. Say I should label it probably, like these are the rows 1 2 3 and so on. So if d row is positive, we are moving down because row is increasing, and the columns are like this 1 2 3 and so on. So if we are moving to our right, the decall is +1, and vice versa also. If decall is -1, we are moving to our left, and if d row is -1, then we are moving upwards. Now there could be a situation where say d row and decall both are 1 simultaneously. So we are moving in this direction. We are moving downwards and towards the left simultaneously. Okay. So now if I pass something like this row and column and this direction, so yes, it would yield a true because this is a possibility. It is a valid move in fact. Same if I say for this, I would have to say d row equals to 0 and decall equals to -1. For say if I have to look through this move, and then I would have to say decall is +1, d row is also +1, and it would return true again. But now if I pass something like d row is -1 in this direction, it should not return true because there is no valid move. Even if I place my white disk here, no blacks would be flipped. And if I did not mention it before, a move is considered valid only if it flips one or more disks of the operand. Okay, so now let's go to the syntax part. Okay, we would be counting the number of flips along with this function, though we have devoted functions in the ahead of the code also. Int r equals to row plus d row and int call equals to d plus decall. You can relate to these because d row is how the row variable row variable increases, and c is how the column variable increases for r more than equal to 0. So, and okay, let me first explain why these things are added, these three, the argument part here. So these are nothing but safety checks, sort of safety checks. You can say I first say that r should be more than equal to 0. For example, in our code, while checking if r sometimes goes less than 0, then it is obviously an invalid move. It should not return true. Fine. And similarly for c more than equal to 0, r should be less than equal to size, obviously, and here also. And grid RC equal operand. So this is the most important part. Our function starts from here only, and it traverses all the disks in the direction given as d row and decall. Fine. And it checks if, for example, if I say decall equals to -1 here, and I pass this disk as the argument, it would first check this if this is the operand here, and grid RC equal operand. So if this is the operand, it would run, else it would not. And similarly for others too. Flips plus plus r equals to to r plus d row and c equals to c plus d col. This is concisement of the code again. Okay, so let me simulate this process at least once so that you get a clear understanding of what's happening. It would first our say 1 2 3 4 5 and this is 2. So here the row comma column is 2 comma 5. Okay, we are using 0 indexing in our program and here I am explaining it through 1 indexing. Don't be confused, it is just for your better understanding. Here the row comma column of this white disk is 2 comma 5. So I would pass my arguments as 2 comma 5 and I right now want to check like with d row equals to 0, d row equals to 0 and d col equal d row equals to 0 and d col should be here -1. Fine. So let us simulate the loop while r more than equal to 0. So r doesn't change because r plus equals to 0 and 0 is 0. 0 is 0. So it doesn't change. So we do not have to care about that. We just need to think about these two functions, these two commands, c plus equals to d col and flips plus plus. Now our row initially, our column initially was 5, and through this command col plus decol, our c, there is a variable c which represents our present column. The row and col represent the row and column from which we started, and r and c represent the rows and columns which we are currently at. So now you can say first our c would be col plus decol, which is 4. So initial c would be this, and it would check if this the grid rc is equal operand. So if this disk is operand, it would continue, and yes it is, it would continue the loop with flips plus plus and c plus equals to d column. So initially flips was 0 and flips would be made 1 here. C would be made 3 after this step. Fine. And it would continue like this till C is made 0. It would come here. After going through all of these, flips would be equal to 3. And when it lands here, it sees that it makes C as -1 actually, because C would be 0 here by 0 indexing principles, and by C plus equals to decol, the C would turn to be -1, so it does not run the loop once again because C is more than equal to 0 here. So I think you got the concept now. Towards the end of this function, we see there are return statements. These help us to return the value. We can see the return type of this function was int, so we need to return integers only. Now first it checks if the flips are more than 0 and the safety conditions once again. Okay, so most importantly, it checks that grid RC equals to player now. Now this should be our white piece. So the cell state of this this cell would be made as our player, the white. So if these have to be flipped, the state of this cell has to be changed to white. So it returns flips. Now if the flips are more than 0, it returns flips, and otherwise if there are any other conditions which are not met, like safety conditions have been violated or whatever, it would return 0. It simply means a failure of the placement of the disk in a particular direction. For example, if I try to place a disk here, it would return 0 only because it can't be placed obviously here. Okay, now let me explain an important part of this function which I initially forgot, that is ternary operators. It is this line. Ternary operators is nothing but an concise if-else block. So actually, honestly, I wrote my code without using these and using just the traditional if-else blocks. But I realized their importance when my code of 750 lines was reduced to just about 500 just by use of these simple statements. So they are an important part of the whole project and I have used them at several places, so it is better to understand this syntax well at this point only. Now, this is the variable. As we start with the syntax of the operator, this is the variable, the data type and its variable, which has to be initialized or given a value by applying some conditions present in this block. So it first checks if the cell state of player is black. If the cell state of player is black, the player was the argument which we initially passed through the function. If this is true, question mark, if this returns true, then the cell state of opponent would turn white. Else it would be black. So basically it is nothing but I can also read this as if cell state player equal black. If cell state player equal black, then cell state of opponent would be casted white, else black. So logically also it makes sense because if the cell state of player is black, the cell state of opponent is obviously white. And if the cell state of player is not black, means it is white, then the cell state of opponent, the other player, is obviously black. So fine. Now we can move ahead. Okay. So we have another similar function, a very similar one, called as the flip direction. I think we already know about these arguments. These are exactly the same ones which we used previously. So I should not need to explain them again, I think. Now these are again the ternary operator. We would use them quite of multiple times. The same statements again, once again. What this actually does is, the function actually does is, the previous function was just checking if the check direction, just to check that if we can flip the disk. The flip direction does that action. It's the action taker function. Once we have confirmed that the action can be taken, we take the action. We will see as we proceed that we always use the check direction function before a flip direction one, because we first check if the action can be taken and only then we take the action. There is no point of flipping the disk and making an invalid move and then reversing it again. So it increases the efficiency of the code if we first check if the action is valid and only then we take the action. So it is nothing but again we just flip the disk. In this the disks which come into our path during the traversal, like I explained, during this traversal these disks would come into our path. We just change their cell state from opponent to player. Simply this is just flipping the disk, nothing else. Okay, so I think this should be fine. And yes, I don't think I used this void return type earlier, but you know that it does not return an integer or anything else. It just flips the disk, so the data type has been represented as spoil. Okay, so let's move ahead. This is a visual if you could not understand check direction and flip direction very well just through my words. This is something which would help you to understand everything. The flip check direction function just checks if the path is valid. We pass various paths through the function and it gives us the value true or false, like number of flips or return zero statement. And it just checks the path in a particular direction. Fine, the flip direction is the doer function and it flips the disk and we can see the result afterwards. So I think it should be very clear now after this visual image. Okay, now we come to the AI part. And the first function is make move AI. Okay, an interesting thing about this function is the return type of this function is not an integer, string, or any other, but it is a vector. We return a whole vector, which I explained earlier, a tiny array, and the vector is not so simple. The vector consists of elements with the data type move. The move was the structure which contained the row and the column, if you remember. So we would return a vector with its containers having the data type move. Data type of a structure, in fact. So it could be a bit complicated, but try to comprehend it. So make move AI, we start with our function. These are the arguments which you already know. We initialize a vector named as flipped, and the vector contains the variables of data type move again, and grid row comma call, okay, equals to clear, we already know. So make move AI, let me first explain what make move AI does. It basically makes a valid move and then checks if that move is good or not, and we would see another function unmake move AI that undoes this move. So basically we have to explore the whole decision tree. We have many decisions to make. For example, as I explained earlier, we could be left with many possibilities to choose among, and we have to choose among them. So essentially, as we explained, as we like I explained earlier in the video, we would go to each of these. We would traverse the whole tree by some pruning techniques, of course, but we go through each of these nodes and check for their value. Okay, so I need to make some moves. To go through this decision tree, I need to make moves. I need to flip this and check what the condition is right now and how the board looks. I need to implement that evaluate function, call that evaluate board function again and again. I don't think I have introduced the evaluate board function. Okay, I'll do it in some time. But there's a function called evaluate board which gives our score. So I need to call that function again and again at each and every node so that I know what its value is. Okay, so make move AI is just this traversal. It goes down the tree, and we need a function to go up the tree also, because we need to apply the backtracking principles and to go to the other nodes. And that function, that thing is established by unmake move AI function. The make move AI helps us to go down the tree, and unmake move AI helps us to employ the backtracking algorithm, and it moves up the tree. Fine. So now I'm explaining the syntax of this function. Now, okay, this is again a ternary operator which assigns the color of opponent. Okay, why am I writing this again and again? Because I initially said that I am the AI and I am the black. The human is always given the preference and hence is given a black piece to move. So I am the AI and I am playing with white pieces. So the cell state of opponent must be black always. So you might think like this, why am I doing this? But much not like that. I might use these functions even for the human. The human just gives me input of row and columns. I need to make that move. I need to implement them to the board. So I might have to use these functions even for the human. Okay, so that's why I'm keeping it very general, and so I'm using these ternary operators again and again. Okay, for int d row equals -1 d row. Okay, so now it checks. For example, we have to make a move and place our disk here, row comma at row comma call. So basically, I have to check through every direction. Like on my board, there are particularly 8 directions. This, this. Okay, all these 8 directions. and I can flip the disk in any of these directions. So I have to check for each of the directions, and these directions can be represented by dcall and drow variables, and I need to go through each of them. Like drow could be -1, 0 or 1. Drow is -1 when I move, say this is the row and this is column. So drow is -1 when I move upwards. Similarly, I explained it earlier also, and drow is 0 when I move only in the column wise direction, and so on. So when drow goes from -1 to 1 and dcall goes to -1 to 1, we can traverse through every direction basically. Every pair would be taken into account. Are you able to visualize it? I think yes. So fine. We check through each direction through these two for loops, nested for loops we call them. Okay, and if drow equals to 0 and dcall both are equal to 0, like there are three possibilities here of drow and three possibilities here of dcall. If we multiply them, we get a total of 9 directions. But we know that we have only 8 possibilities to move. So there must be one redundant direction. And we find that as drow equal 0 and dcall equal 0. So what this means is we don't move anywhere. So it's totally illogical for drow and dcall to be equal to 0 at the same time. And we hence just skip if this is the case through this continue command or whatever. Fine. So it just continues. It does not execute any commands when drow and dcall become 0 simultaneously. Now, okay. So we first employ the check direction function. We have our drow dcall and we check if there are any disks which can be flipped in the direction which we have right now. Okay. So if this is 0, more than 0, if the move is valid in this direction, then R would be equals to rho plus drow and see, okay, you can see why this was done, because just to like flip the disks. For example, if my drow and dcall both are here, the same thing exactly which I explained earlier, I am going to do this again. I think you can visualize it. I won't need to switch between many slides. R would be made as the next one. Like if I was here on this cell, and if I go to this one, my R and C would be changed accordingly through these two statements. Okay. While grid RC equals opponent if this piece, the state of this cell is equal to that of opponent, this will be switched as the player. If this is the opponent and I am traversing it in my move, this is obviously flipped and the cell state is made as the player. Okay. And yes, try to remember that the return type of this function was vector, and that vector was named as flipped here. So we need to use this function pushback, which I mentioned earlier. Pushback just adds an element at the last of a vector. Okay. So flip.pushback, this is the syntax of using this pushback function in a vector. Flip.pushback row R comma C. So this was flipped, and we make a record that this was flipped. Why do we need to make a record now? Okay, this is an important question. We have to unmake this move. We have to undo this move. I explained the decision tree thing, right? So we are now flipping it, but we are flipping it hypothetically. Say I'm just flipping the disk to evaluate the board at this point. I'm just trying to think like, okay, if I flip this, if I do this move, these disks would be flipped, and then the opponent would do this move, and so on and on and on. So this is an hypothetical scenario, but it is right now happening in the real time, and I would in future need to reverse this decision. I need to employ the backtracking principle, and I would have to reverse this decision. I would have to restore the game to its initial place from where it started before I decided to make this move. So we push back this r comma c so that we get a record of what wrong I did, like not exactly what wrong I did, what all changes I made to the board, so that I can reverse those changes easily. Now what I'll do is I would in the unmake move AI function, I would just traverse through this vector and undo all the changes which have been made, and the record of these changes have been made through this vector. Fine. Again, r equals to d, r plus equals to 0, c plus equals to d call. So it moves to the next state, and it will go till it finds each of, like the check direction comes less than 0 or something, like it comes 0. Fine. Okay. So finally the return statement, we return the vector which we got. I think it's fine. Okay, there was another thing which could have been done instead of using this function, which was to copy the whole board and make the move again. So the initial board, the original board won't be hampered. I would have copied the whole board and made my move on that only. The board initially would not have been hampered, and there would not be a need for a unmake move AI function. So it would logically make the things very efficient, like very simple to understand, but I did not use that approach. Why? So if we copy a whole grid, like which is a 8 cross 8 matrix, it would take a huge amount of storage, huge amount of time, and it would just make our project inefficient according to the time and memory space. So this was the logic implementing just to save some time and memory. Okay. So I think I have already explained 90% of the unmake move AI function in the make move AI only, because the logic must be very clear to you. I am not going to explain these arguments again and again and these ternary operators. So as I said, we just traverse through this disk. Okay, there is a new syntax here actually, which should be taken care of. This is called a for each loop. So this is basically nothing but for const auto is nothing but const auto is like a data type which automatically detects function or data type, whatever you call it, which automatically detects the data type of the variable followed by it. Okay, so we don't need to think about if f is int, string or whatever. So for each loop essentially uses this function for determining the data type. So we say that for auto and f belongs to flipped. Okay, so for every f belonging to this vector flipped, grid f dot row f dot call equals to offline. So okay, it is passed as an auto here, but we know what its data type is as suggested by our id, which is const move and. So the auto is replaced by this move in the time when the compiler compiles the code. The data type of this f is move. That was the structure, and we call the structure variables through this dot. So this is a structure, and I need to call the variable row from the structure. So I would say f dot row and f dot call for this. And I do nothing but just replace the changes which undo the changes which I did earlier. Do you remember that I made this f dot row f dot call as player here? See, grid rc equals to player. So I'm just reversing that change to restore the board into its original form, so that another set of decision tree, another set of decisions can be taken and compared with these. So I think it should be fine. Okay, let's go ahead. Okay, once again, if I was not very clear through my words, I think this image would make it perfectly crystal clear everything for you. This is how our make move AI and unmake move AI cycle goes. This is the original board say the make move AI just makes a move, places a disk somewhere, and it checks the value of this disk. It calculates the score of the board here through the evaluate board function, which we would see. It employs the Minimax algorithm, and we use the unmake move AI function in it to restore it to the original position so that we can go to some other position from it. So basically, say if I can move here or here or here. For example, just in a hypothetical scenario, if I have these three options, I would first place my disk here through the make move AI function. Okay. I evaluate the board here and I calculate the score to be 2 here, say. Again, it's an hypothetical scenario. Okay, then to place my disk here, I would need to check what the score would be if I had placed my disk here. So for that purpose, I would reverse this decision. Reverse this decision by calling the unmake move AI function, and this would be made empty again. Then I would call my make move function again to place a disk here, and I evaluate the function again. Say it gives me a value 4 this time. Okay, so I am storing these values 2 and 4 in another data type. We will discover it later. Now I again naturally call the unmake move AI function, and this cell is also made empty. Then I call the make move AI again, and our disk is placed here. Say it gives a value of 1 here, and we call the unmake move AI function again, and the whole cell state, the whole board is restored to its original position. But we have got the values which we would have been attaining through these moves. So I would say we are the maximizing pair. So we take this value of 4, and I place my disk here because it was the node which gave me the maximum value. So here this was a very simple explanation because it was running only till depth 1. If you could visualize the decision tree now, it was running only till depth 1. I just saw which of these positions give the maximum score. I did not explore the decisions made by my opponent again. Like this node giving a value of 1 could be a better one actually. Say what if I place my disk here at a position which was giving me a value of 4, but my opponent makes such a decision that it returns a score of 10 for him. So it won't be beneficial for me to make this move. It could, right, this is a hypothetical scenario again. So we will explore it to the certain depths later, but this was just to explaining. Fine. Now let's move ahead. Okay. So this should be very simple now when we have gone through the logical blocks. This is nothing but syntax, the initializer list. This is the initializer list. Okay, so we use the initializer list. When do we use it? In the class constructor. This is the constructor and it is suggested by its name only. The name of our class was board, if you remember, and the same is the name for constructor also. So this is the initialization list. I explained it earlier also through the pair class, so I won't waste time here. Now this is something which initializes the board. Okay, you can see int center is size by 2, the center of the board, and these, okay, if you remember, I mentioned in the starting only in the rules part that there are always 4 disks in the order black, white and black placed in the center 4 cells of the whole board. So this does nothing but just employ this rule. Okay, you can see. Fine. So let's move ahead. This is another function which prints our board to the screen. We are analyzing everything on the board. We are making changes. We are employing certain functions, but we have to print the board for the user and obviously me to see it. Okay, so these are the loops which we use to quite trivial things. Still, I might go into explanation of these also. You may skip it if you want to. This part is going to be too trivial. Okay, so count slash in. This is you- escape sequence. This is known as escape sequence if I remember well. This is just an operator which adds a new line to our output. Okay, for char c equals to a c less than a plus size. Okay, one important thing which we got was we are using character arithmetic. This is a character and this is an integer. How come are we adding a character to an integer? This is a nice question if someone would have thought about it. So it's not actually like that. We are just adding the ASCII values of both. The ASCII value of A is 97. No, sorry. The ASCII value of small is 97 and capital A, if I remember correctly, is around 65 or something. But okay, that doesn't matter much. We are just adding the ASCII value, we are just adding this integer size to the ASCII value of A, not the character A. Fine. This is an example of implicit typecasting which compiler does itself without an external command. We are not saying that take the ASCII value of A to the compiler anywhere, but it's applying its common sense, you can say, to convert this A into its ASCII value and then add size and C. And the implicit typecasting is done again by the compiler when he sees that there is a variable of type character here. So he changes that ASCII value into the character again to assign the value to this C variable. Okay. So what we do is basically we travel through this A, B until size for 8 and say this is an ASCII value of 1, 2. So 8 is I think F. Yes. So we just travel through A, B, C, D and F we count that output that into the screen. So this line A, B, C, D, E, F in this order gets to the screen, gets outputted to the screen. Okay, so now we use other things to like if you see the output window, there was something padding here after A, B, C, D, E, F of plus and minus signs. So we print that through this. Okay. The important part here again, you can see what this does and how it functions. I am not explaining it right now because it would unnecessarily extend our length. I would explain the most important part, which is setW. So setW is a function from the IOmanip library and it sets the width. Basically, it organizes our board very well. Otherwise, it would have looked very weird. I can't like even imagine how it would have been. But this sets width as 2 for every of these 1, 2 and 1 till 8 column numbers, so that they look structured and they are in line with everything. The alignment is perfect, basically is ensured by this function only. Okay, so I think you know already these things. Fine. One thing which I should mention here is we are using 0 indexing only, but we are using 1 indexing for the user. Actually, computers are familiar with 0 and 1 only, and we use 0 indexing here for the computer to be familiar with it. And honestly, I am also more familiar with 0 indexing because I am a programmer. Else, for normal humans, the counting starts from 1 only. like 1, 2, 3, 4. So I am displaying one index row and column to the user for a better GUI, uh, better interface, but I am using zero indexing for me. Okay, so this shouldn't be a ground for confusion. Okay, let's move ahead. We have another important function named as isValidMove. It checks if a move is valid. Okay, so for example, if I input something like I did earlier when we were going through the project overview, if I entered a invalid move, the move which cannot be made into the board, then this function should return a value of false, and I would have to run it again and again when I take the input of the user, so that I can run that exception handling block. Yes, we would learn exception handling in some time. We would see how. Okay, so is valid move just checks if a move is valid or not. First, again, those safety checks, as I mentioned, the column, row and column should be greater than 0 and less than or equal to the size. Fine. Okay, so first this new condition has come into place, and let me explain what this is. Grid row comma c is not equal to empty state empty. So basically here arguments are the row and the column which the user has entered, and he wishes to place his piece black, that is he wishes to place the black piece at this particular coordinate row comma col, and we check if the cell state of this place row comma col is not empty. If the cell state has been already occupied, the cell has been already occupied, we cannot obviously place another disk here, so it would return false straight away. Now we go to the logic. We employ the check direction again as we did earlier. Fine, we go through all these combinations of d row and d col, and I explained this redundant case earlier also, the 9 and 8 thing, and we use the check direction function again, and if it's true in even of the one direction, then it returns true. For example, we check through all of the 8 directions. Fine, we check through all the 8 directions. If it's true in any of the one direction, basically this function would be called 8 times. At max 8 times. It could be less than that also. At max 8 times this function. And even if it returns true, it returns a non-zero value greater than, obviously, value greater than 0 even once, the whole statement would return true, because there is at least one direction in which the opponent risks are being flipped, so the move is valid. Fine, I think you got the logic. Remember, the syntax, the code, everything is subsidiary, it is secondary, but the most important thing in every project is the logic. So try to be with me for the logic part. Okay, there's a concept called early exit, and it is also known as short circuiting, which I have used here. See, I have used this return command 3 times. Now one could ask that will this function return 3 times, and how can it? Like, it can return only one time, right? I can't write return 0, return 1. No, it's not possible. But this is not the case if you are thinking like that. See, if this is true, if these conditions are met, then it would return false, and it would not go to these lines of code. It would just short circuit our code from this brace to this brace. Fine. Okay. Similarly, if these conditions are met and it returns true here, it would never go to this part of the code, and our function would be short circuited from here to here. Fine, so this is why it is known as the short circuiting of code. And why did we need to add this statement here? Because there is a possibility that neither of these statements or of these are met. Fine. Even these are not true, and the true has not been returned here. And these are also not true, so our function does not return even false here. So our function has not returned anything here. But there would be an error if this is the case, because function needs to return a bool value. So if it does not return any of these, and these are not short circuited, so it would return false in the end. Okay. So essentially our compiler goes to this command only if these conditions are not met, and if these are not met, it returns false by default. Fine, let's move ahead. Okay, so this is a make move function. It is different from make move AI function. First of all, don't confuse it with the make move AI. This is the function used for the human to make the move, and this would never be reversed. We are not creating a vector here. We are not returning a vector here. We don't intend to reverse this move. This move is being made permanently. We would use this function to make move permanently. Fine. Okay. So first it checks if the move is valid or not. If it is not valid, then it returns false straight away. I think I forgot to explain this not equal to sign and a variable after this earlier. My apologies for the same. Now let me explain it here for attention here. This is optional of course, but let's say. So if I write this statement and an else block after that, so it means that if x is more than 0. So basically it is the principle of if else statements. They take boolean variables as their arguments and they always run through these. Even if you write x is more than 1, these conditions like this in the if block, these are converted to boolean values. If x is more than 1, then that boolean value would be 1, else it would be 0. Fine. So okay, so here also if I pass an integer or let's say I am passing a bool here. So if I pass a bool and its value is 1, basically greater than 0, if x is an integer and its value is greater than 0, or if x is a bool and its value is 1, then the if block gets executed, and if not, then the else gets executed. Fine. Okay, so if I add a exclamation mark here, so what does an exclamation mark represent? It is just the not operator, not operator. Fine. So this says if x not 1. Okay, so x is not 1 means x is 0. We don't have a way to write x is 0 just as simply as x is 1. So we are a not operator here. If x is not 1 means that x returns a 0 value. Then this gets executed. Fine. Else this one. Okay, so here also is not is valid move. So if is valid move is not equal to 1. Like if is valid move, this whole is false. So, that means the move is not valid. Then it returns false straight away. Again, we use the short circuit theory. Okay. So firstly, now after we have checked that the move is valid, we need to place the disk here and we need to flip the disk. Our player has chosen to place the disk at a certain position. Then the compiler or I have to do two things through my program. First is to place his disk here. Change the cell state of this cell to that of the player, which is established through this command. Okay. The other thing which I must do is flip all the disks that can be by placing the disks here. Fine. And that is done through this. Again, we go through each of the combinations of derow and decall. We skip the 0,0 case. I did mention earlier during the explanation of flip direction and check direction functions that we would always call a check direction function before a flip direction function to check about the validity of the action which we are taking. Okay, so I call the check direction function first to check if I can move, if I can flip the disk in a particular direction. Fine. And if I can, if this is more than 0, then the flip direction is executed and all the disks are flipped, and we saw how these functions work earlier. Okay. So fine, it would flip all the disks because it goes through all the combinations and there is no short circuit here. So the loop would always run completely. Okay. And it returns true by default. If even one of the disk is flipped, it returns true, else it returns false. Okay. Now these are relatively simpler functions for me to explain. Count disk is nothing but it counts how many disks are there on the board right now. We initialize two variables, black count and white count, both as 0, and we would increment them whenever we encounter a black or a white disk respectively. So it goes through the board, these two nested loops. This is a traditional way of going through a 2D vector array. So these variables help us to go through the every cell of our board, and at one cell, if we find that the color of that cell is black, the cell state is black, we increment the black count, else we increment the white count. And this function, okay, an important thing here is the return type of this function, which is pair. This might be a new data structure for you, so let me explain what it is. So pair is nothing but a data structure that can store two values, just two values, and it could be of any type. It doesn't need to be of integer. Like here it has to be, but not all the time. Generally it can be of any data type. Here I've used int, and so a pair is returned here. Black count comma white count. This is returned as a pair. Pair is nothing but a data structure which stores two values. Fine. Okay. This is get valid moves. Okay. I would explain why we use this function, why we even create this function. Get valid moves is nothing but it prints the set of valid moves available for the player. I initially thought that I would add a utility, and I might right now, to display all the valid moves which a player can make to assist him to make moves faster so that he doesn't have to identify it. And it could be used there. But here we use for our AI part, we feed these get valid moves into the AI, and so this is basically the do you remember we expand the node? We first see what its children are. So this is basically that function which generates all its children. Okay, so I am at this node right now, and I need to see where all can I go. I can go here, here, here. Like I could place any disk anywhere, but it's not like that. Like my function would, if make move AI, if I pass all the 64 squares through that make move AI function, it would be very inefficient because I need to just check the valid positions, and get valid moves establishes this purpose. It makes my AI know about all the valid moves it can make, and only those valid moves would be passed through that make move AI function. So yes, how we get the valid moves? I think it should be quite simple. So we basically try to check every cell if we can place a disk there, and if its valid moves come true, this function, the value of this function comes true, then we push the value of this structure into our vector move. Fine. Okay. And finally it returns the vector moves. Okay. Fine. Let's move ahead. Count flippable disks. Okay. This is a function which is used in the evaluation of the board. Like if I place a disk anywhere on the board and now I need to count how many disks can be flipped in all the directions. I need to look on all the 8 directions and how I need to add the disk flipped in all the 8 directions. For example, place my disk here and I can basically flip 4 disks in this direction, 2 in this, 4 in this, and so on. So the total number of disks which I can flip by placing my disk here are the sum of all the disks I can flip in taken in all the 8 directions. So this is what this function does. Yeah, again, it travels through all the combination of these directions and uh, we returned the flips, the number of flips through this function. If you remember, we did not use it till now, but yes, the number of flips were returned there just to use it here. So total flips is incremented by the value of the number of disks flipped in this particular direction. Fine. And the total flips are thus returned. Okay. Okay, so now the implementation of the algorithm and the heuristic part actually begins. The evaluate board function, I did mention it a lot of times earlier also apparently, and I'm going to explain it right now. This is the board which gives the score to a particular position. Okay, this function gives the score, gives every board, every position a particular score. And how that score is given, let us see. Okay, let's first think about how can we evaluate a board in Othello. First thing would be like I could just count number of my discs, count the black discs, count white discs, and take a difference and see how it is. That could simply be my score. That's a very naive idea actually, but still you could think like that. Okay, if we dive deeper into this theory of Othello, we see that there are parameters such as mobility and the heuristic table which we earlier figured out, if you remember, that gives code to every cell. So we think like we need to use those also. These things like also the heuristic table and the mobility. Mobility is the number of moves which you can make at one point. So it's quite important. And through this function, we combine these parameters of mobility, heuristic evaluation, and the uh, heuristic and the parity. The discount that the difference which I mentioned earlier is known as the parity of the board. The black disk minus white disk here. So we do this. Okay, one more important feature of this function is it also sees if the game is an end game. Like for the whole game, we would be focusing on enhancing our position. If our position is enhanced, then the number of disks could be increased anyhow. That doesn't matter much. But towards the end game, when the game is about to end, and this was like there are total 64 moves, so when there are only just 12 moves left, so it says that the end game is near. So like that. But if the end game is approaching, we would like to not focus about the position but the parity of the board. Like we are going to be ending the game, so we would now want that the number of discs that the number of my discs should increase, and I'm not focusing more on nothing else. Okay, so we just through this function we just combine all these parameters, and if you remember during the explanation of A star search algorithm, I mentioned about the weights w1, w2, etc., which we give to these functions. Like we have particularly three parameters here: the mobility, the heuristic evaluation, the heuristic board and the parity. So I give the weights W1, W3, W2 to these parameters, the heuristics, and and I combine them to form a larger heuristic. Fine. And I evaluate my board according to this heuristic, which is a combination of these smaller ones. Fine. So only this is implemented in the code, and there is no new syntax or data structure which I need to explain here. I think everything is quite simple. Okay. So fine. This is the visual which would help you to interpret the logic even better. Uh, as I mentioned, there are positional weights, score, and the parity, which we combine through, say, something known as adaptive weighting, and we give weights, certain weights to all these. And yes, here it is mentioned that towards the mid game, we give more weights to the position and mobility, but towards the end game, we rely on the count of the disc or the parity more than the position or the mobility of the board. I have already explained the algorithm before, and very in each detail of algorithm has been explained, and you can go back to that section of the video if you want to revise it before coming here. I will first explain the function max value. Basically, in this part, we have three functions, which is first is max value, the other is the counterpart min value function, and we have a new type of function which is called as find best move. So I'll explain all three of them properly. Okay, so first of all, you must be clear with this pseudocode that I had explained, and by following this pseudocode only, I have written the code for this algorithm implementation. Fine. So let's move ahead. So first, in board max value, first of all, in my code, I had declared these functions max value and min value before this find best move function, and but now I am defining them after that. It is possible in C++, as you might know. So I am just to indicate that this max value function from board is being defined, I use this operator. Fine. This is I think access specifier operator, so I'm using this operator to okay. Now you can compare this implementation in C++ with the pseudocode, and the most of it would match, and where it doesn't, I would explain it. So here we had with arguments as S, alpha, beta, and D, and similarly we have arguments as alpha, beta, D, and cell state pair. So our S in this pseudocode becomes the cell state of the pair. I think you can easily visualize it because S was the node in the decision tree, and that node in our Othello decision tree, as I explained, was the cell state. Fine. So okay, so this cell state could be white or black right now, but the node represents the state of the whole board. Fine. So now let's start with this function. If depth equals 0, return evaluate board player. Fine. So first thing is we are not we are doing one thing different from this pseudocode. Here we were incrementing the depth, and we were comparing with the depth with the max d, and if it becomes more than max d, like we have exceeded the limit which was given to us to search till a particular depth limit. So if we have exceeded that, we return the valuation of x. But here we are given the depth here only, the limit depth max d, and we decrement it as we move on. So when it becomes 0, like we have traveled through the depth, it returns the evaluate board function. We have defined the evaluate board function already. Fine. Okay. So this is a vector valid moves. I think you know this. Like this is the data type vector, and it contains the data type move. All of its containers have the data type move. Okay. So get valid moves pair, we have defined this again before only. So if is valid moves is empty, means that the current pair does not have any valid move. First, we evaluate the cell state of the opponent by this ternary operator, and then after that we check if the operate moves are also valid. Well, sorry, the get valid moves opponent is also empty or not. If it's empty, it means that the game has come to an end. Neither of the player has any move to play, so it simply returns the evaluate board. Fine. Else, it will return min value depth with depth -1 because we have already traversed one depth, and alpha beta comma opponent. So alpha beta are dynamic quantities as we saw, and cell state would be opponent now. Fine, because opponent has to move. One thing, we are passing min value function through this. I think you would get this easily, but still if you are not able to, we are passing min value because our turn, we were the maximizing pair and our turn is over. Like if our turn is over because we didn't have any valid moves to play, so the turn is switched. Now the turn passes to the minimizing player, so we are passing this through the min value loop. Fine. Okay, so let's move ahead. Int value equals to int min, just like we did here. Further on, the algorithm almost matches with the pseudocode. Our implementation almost matches with the pseudocode as we see. So we define value equals to int min, like here. And okay, again for all the nodes belonging to valid moves, C, exactly the same thing. For C in children S and for move in valid moves. Okay, exactly the same algorithm. First we calculate the cell state of the next player. Again, it's the cell state of the opponent, same thing. And we make a temporary move through this function, make move AI. I think you can get why this line works for all of these two, because for example, first we evaluate what min value is. Min value C alpha beta D plus 1. Again, we are doing D minus 1 here instead of D plus 1 because we are decrementing D. Same logic as I explained it here. Okay, we are decrementing the D because we have been given the max D value in this function in depth. This is basically max D, and we are decrementing it as we go down the tree. Fine. So basically we are here, we were tracing till what depth have we gone till now, and during the implementation we are tracing what depth is left from this point. Okay, fine. So max value, so basically I was explaining how these two lines were converted to one single line in the implementation to make it simpler. So if v dash is more than v equals to v dash, else if v dash is less than v stays as it originally was. So this is what this one line means. So basically if we see, v always takes the value that of the maximum of v dash and v. Fine. So v value takes the maximum value of value and the min value, this thing. Fine. We have assigned the best value to this variable value. Now we undo this move, and this was just a hypothetical scenario which allowed us to go down the tree and process for the maximum value this variable could attain. Now we have to go back to analyze other nodes. So we undo the move by using this unmakeMoveAI function. Fine, we have defined it already. So, and these two alpha beta pruning commands here are implemented in the code as it is. If value is more than equal to beta, then return value, and if and same thing. See, that is again the concisement using the max function. Alpha equals to max alpha comma value. So if
alpha. If the value is more than alpha, then alpha is set as the value. Uh, Else it remains the same as it was before this line one. Fine. And it finally returns the value. Okay. So you have got the implementation of max value well, I think. So there shouldn't be a need to explain the min value function because there aren't much changes. If you see, like only these things change, like there would be a max instead of min here. Some inequalities would change, the alpha beta would be switched, and there's nothing much to explain here after I've explained the max value function. Fine. So now let's go to the third one and probably the most important as we have not covered it so far. So find best move function. Now this actually will be the function which we will be using every time to find the best move. We would be calling this function only, not the max value or the min value ones, because this combines the logic of these alpha, beta, pruning and minimax algorithm and gives a concise value of the best move, the concise best move. Fine. So, okay. So this is nothing but the vector of valid moves, and if valid moves is empty, obviously the best move would be -1 comma -1, that is the move is not there is no valid move. Fine, it just indicates that there is no valid move. Now we have to maximize the score. Now you would feel that when I am giving hints, so my cell state would be of the operand and that is the minimizing player. So I should be minimizing the score instead of maximizing it, what is being done here. But this intuition is not very correct because when I imagine myself from the point of view of the other person also, I become the maximizing player. I hope you can get what I'm saying. Basically, I would be aiming to maximize my score again. Fine. So from whoever's point of view I am seeing the game, I am minimizing the opponent score and maximizing mine. Fine. So this is just an initialization command for the best move. If the valid move is not empty, then it contains at least one element, of course. So the best move is initialized as the first element of this vector, valid moves. And again, the same thing, we initialize the alpha and beta. Okay, one thing you might have noticed is we did not initialize the alpha and beta here. They are always initialized while they are called, like this. So they are called using this find best move function in our project. So we initialize them here only. And why did we initialize them like this only? Like we give int min to alpha and int max to beta. So what was alpha? Alpha was the minimum guaranteed score that the maximizing player would get, and beta was the maximum guaranteed score that the minimizing player would get. So basically alpha is the maximizing variable and beta is the minimizing variable. Okay, understood. So we have to assign alpha as int min and beta as int max for them to act in specific ways. Okay, let's move ahead and see what this function actually does. So for all move for each loop, this is for each loop only. So for a move in valid moves, cell state next player is this, again a simple ternary operator. Now we are quite familiar with this. So it assigns the next player the cell state according to what the cell state of current player is. Fine. Vector move flipped equals to make move A. Again, we make a temporary move and we assign a score to that. Here, this is the key command. Int score equals to min value def -1. So basically we figure out what all possible moves we have. We take one out of those and then we apply the minimax algorithm on that with depth -1 as we have gone to the depth 1 already.
and then we we call this function unmake move AI to reverse that move. So basically we are iterating through all the possible moves at depth 1 and checking which one is the best one. Through this, if score is more than best score, then best score becomes score and best move is move. So we get the value of score of each node after the parent node, right? And we choose the best out of them. And we assign them the values of best score and the best move. Fine. So this would be the statement which would be used, and this best score equals to score is not used externally by the program, but internally it holds importance because this is what is being compared in this if statement. Okay, so if I don't update this best score and keep updating the best move, it would be updated only once and this loop would would stop running. Okay, so I need both of these statements, but this is only used externally. Okay, so alpha equals to max alpha comma best score here. That is, our AI is interested in the highest score it can guarantee. Fine. So alpha is updated to the maximum of its current value and best score can be found so far. So beta cutoff here is not strictly needed because this is just the root node on which we are analyzing, and we are maximizing directly by selecting the best move. So the pruning basically happens not in this one, not in this function, but in the Minimax algorithm. Okay, here it is done here. So okay, one more question could come to your brain, like we are using only the min value function here, so what significance does the max value function hold? So again, let's go to the min value function to solve this query. The min value function in itself calls the max value function. This was the core logic of our project, the cross recursion, and this is something we use here again. So basically, even if we use just the min value function here, it on the surface seems like max value does not hold any importance, but as we go deeper, the min value function itself calls the max value. So both of the functions are equally contributing to this working of the algorithm. Fine. Finally, it obviously returns the best move. So we are done with the algorithm part, and now let's continue with our code. Okay, so now we start with the third class of our project and the last one too. Again, we have the access specifiers, public and private, and we have three objects in this class called as board, two players, and something called as current player. So the board belongs to the board class which we initially defined. Both the players, player 1 and player 2, are from the player class. And basically these are the co-objects. Basically, you can say that these belong to both of these classes, game and board, and these objects, player 1 and player 2, belong to the game class and as well as the player class. Fine. So basically we have two players in the game. Player 1 should be set as default to human, and player 2 can be either human or AI. So essentially the match can be between two humans or an human and an AI. Fine. And this object player star current player is a pointer in its data type, and we will get to know how it is used further when we go to the video. So right now let's move to the first function of a program. Basically this class game would be orchestrating the flow of the project. We would be taking the input from the user and giving necessary outputs. So it integrates the board and player objects to create a playable game, and that's what it does. So this is the first function and its return type is move. So fine, get player move string input, we declare a variable with data type string and we ask the user to enter its move. And this is something new, get line sin.input.
So this is nothing but a substitute to traditional commands like scene used to take input from the user. Where the difference comes between the getLine and scene is that getLine takes a whole line of input and sets it as the value of this variable, whereas scene takes the values separated by spaces on new lines. For example, if the user enters something like ABC, then a space or a new line, and then something else like DEF. For now, assume that this is just a space, not a new line. So user enters something like ABC, space, and DEF. And we have written something like scene, and there is a variable with data type string declared before that, obviously. So S would assume the value of only ABC. Okay. But if we use this getLine scene dot s comma s, s would assume the value of this whole string, whole line. So this whole line gets stored as the value of this variable. This is the use of getLine, and here we use it just to counter the cases where the user might enter spaces between the moves, or it might enter some spaces before that or even after that. So these are something which we need to take into account while running our code, so that our code is not interrupted by these exceptions. Fine. And this would be the main aim of the game class. As you see, we would be taking care of various exceptions that the user might enter, and we would everywhere prevent our program from running down. Okay. So first of all, now when we have stored this value of this whole line into an input, we need to clean it. From cleaning it, I mean we need to take out the important data from it and just process that. We need to ignore all these insufficient things like spaces. So we use these two functions, input.erase, basically first same function but with different arguments. So we use this function input.erase. The first line does nothing but delete all the preceding spaces, like all the spaces before the first character in the string. It deletes all the spaces. Fine. This is not just a syntax, so there's nothing much to explain. They are just rules in which we have to write this function in. And similarly, this statement removes all the spaces, blank spaces, after the last character. Okay, so we get our string something like this after this, the execution of these functions. Okay, now we check if the length of input is 1. So basically we have two possibilities if the assuming the input is valid. Either it could be h or something like a1. Fine, this is just an example, or something like a1. So if it is h, then its length must be 1. Fine. And this is again a function from okay, so this is again a function on the string.length, which just returns the length of the string. If I didn't mention these getLine and input.erase and everything like input.length are from the string library. And so the string library is the one which enables us to use all these functions. Okay. And this is something new function. So this is called as toOpper. So basically if user enters something like small h, but we have to again we have to like maintain uniformity in the code. So we would convert this h into capital H, small h into capital H, and check if this is true. So first the length of input is checked, and input 0 is nothing but the first character only. So first character is converted to uppercase, and then it is checked if it is equal to capital H, and it returns -2 comma -2 after that. Okay, by only -2 comma -2. This is nothing but just an indication
that user has asked for a hint. -2 does not here does not hold any significant numerical importance. Like I could have written -3, -3 also. There was no problem. It was just to indicate that user has asked for a hint and we have to execute and implement those statements in which the hint is provided to the user. So basically it should have been different from what a row comma call could be. Like I would have avoided a 0, 1 or anything like that so that it does not collide with any other argument. Okay, so whenever I see -2, -2 being returned by this function, I know that user has asked for a hint. Fine. Okay. And if input.length is less than 2, it returns -1, -1. So basically, if input if it's less than 2, it could be either 0 or 1, and it is not edge. As if it would have been edge, this statement would have already been executed and short circuiting would have taken place. But if that was not the case, it would return -1, -1. So again here -1, -1 is not numerically significant, but it just indicates that the user has entered a invalid move. So whenever I see -1, -1 being returned from this function, I know that I have to tell the user that you have entered an invalid move and please re-enter or whatever. Fine. Now let's move ahead. These are some variables which we are already familiar with. So basically, if the user has entered something valid, okay, not right now, I should say that, but fine, we first take the call and the row variables. We extract these variables from a string, like a string could be like this. So first of all, call is input from this first character, which could be from A to H. And here in this line, we again use the implicit typecasting, something which is done by the compiler itself. Typecasting is nothing but just conversion of a variable of one data type into another data type. Fine. Now to open input 0, again, if something like A has been entered by the user instead of capital A, then it would convert small characters into the capital ones, lowercase to uppercase by this function to upper. And here we analyze the first character only to get our call variable, and we subtract a character from it. Now this should not be unusual for you because I have already mentioned what will happen here is nothing but these will be converted to the ASCII values, and the difference of ASCII values would be taken and stored as the value of this variable call. Okay. Now to define row, to see what row was, we run through these statements. I'll explain what they are. This is actually a very important part of our project known as exception handling. Exception handling basically deals with all sorts of inputs that a user might enter. We should be able to protect our code. Basically, user should not be able to enter something that makes my program collapse. Fine. Now here if user enters something like from 1 to 8 instead of 1 to 8, it enters something like 9. My program would stop then and there only, but I should ensure that it does not. And there could be many other possibilities, and we ensure that our program runs smoothly through this try and catch block, which is a core part of exception handling. Fine. Now row equals to stoi. This is another important function from the string library only. Stoi input.substring 1 -1. Okay. So basically stoi is an explicit typecasting function. The compiler here does not typecast by itself, but we do externally by this function stoi. So this first takes the second character input.substring through this function input.substring 1. so the second character of the string, and it subtracts 1 from it. Okay, because we are using 0 indexing at our backend. However, 1 indexing has been used for a better user interface at the front end. So we subtract 1 from it and then convert it into integer. Okay, so if I enter 1, my row would be stored as 0. If I enter 2, my row would be stored as 1, and so on. And this STY would fail if a user enters something like A and then an A again. So this would fail because it can't convert a character A into integer by explicit typecasting. Okay, so it would fail and it could give a runtime error or something like that, but we need to like we need to be able to handle this error, so this should not cause our program to stop. So we use this catch block. Basically what happens is compiler first evaluates if this condition would run smoothly or if it throws any exception or an error, and if it does, then the catch block is executed. Okay, in this case it would return a -1, if this fails. If this block of code fails, then this block of code runs and it returns -1, here. So basically again it indicates that an invalid move has been entered by the user and he would have to enter it again now. Okay, so now return row comma call. Okay, if nothing has been returned till now, like user hasn't asked for hint or -1 or an invalid move hasn't been returned till now, it would return the row comma call. Fine. And row comma call would be returned only if they are stored properly through this block. Okay. That was not very difficult. Now we move to the public section of our game class, and first we find a constructor here. I already explained what a constructor is. Again, you may notice that this function again has the same name as our class, and this is the usual initialization list. Let me explain it a bit. So basically the board is initialized by the function in the board class, the board constructor. Player 1 is initialized by these strings n1 and n2, and the self state of player 1 is stored as black by default, and similarly for player 2 it is stored as white by default, and sp2 is nothing but a boolean value which indicates if the player 2 is human or not. So by default it is stored as not human. Okay, and level is stored as 0 by default. Int level was something like the level of AI, 1, 2 or 3 if you remember, and if it's none of them, neither of these, then AI isn't used actually. Okay, and the most important thing in this constructor was this. Although we initialize it again later, but still to visualize it, you can see the current player, the pointer. The pointer here was, see, this pointer here is initialized as a reference. So pointer is essentially a data type which is used to store the reference, the address of some other variable. Fine. And here we use it to store the address of this object, player 1, and is the address of operator, the common address of operator that we all know. Okay, so now let's start, and we start from the start function only. So the return type is void. At first it enters a message to start the game. Basically this is, as the function name suggests, a function which essentially starts the game. This would be something that we would be writing in the main statement of our program, the int main, as you see. So this is the whole starting of the project, and here we have declared certain variables and we see their use as we move ahead. While true. So this is an important part, and it would come into specific places, many places in fact, as we go ahead with this class. And let me explain it a bit right now only so that it is quite clear. So basically while true is something which would run till infinity if the statement called break is not executed. So while true runs every time, but it stops only when it encounters the statement called break. Okay. So if we don't write break or we forget to write break in our program at anywhere, then this loop would be like run till infinity a lot of times, and it would certainly damage your memory or space or something like that. Now, so first of this is our loop. We to take every input, like to take a move or to take this H or C or to take the levels, we will use this while loop only, and the mechanism would be same. So but it's better to understand it here only at the first point so that it becomes very easy later on. So first it enters choose mode, either human or computer. And again we have used the getLine function to get the input from the user. And we store it in the variable input. It was declared here. If input is not empty, I explained these type of if statements earlier only. So if input is not empty, this is again a function only from the string class. Sorry, string library. So if input is not empty, this is the not symbol again. Char first char equals to upper input 0. Fine. So basically this takes the first character of the input by this indexing. So if I did mention it earlier, a string is nothing but an array of characters. So we can use indexing freely even in strings. Okay. So to upper input 0, we just take the first character of the string and convert it to the uppercase and store it as the value of our variable first char. And then we analyze what first char is. If it's H or C, then choice, the variable declared here, the choice would be stored as the value of first char, and it would break. The loop would break because we have taken the input from the user. We no longer need to run this loop again, and the loop should break. Okay. And if it does not break, for example, if this first char if this first char was not equal to H or C, then it won't break and this line would be printed to the screen that your input is invalid. And I think it's logically very simple and correct, because if it is not H or C, then obviously the input is invalid and this should be indicated to the user. Fine. Let's move ahead now. Now when we have stored the value of choice, okay, let me once show the simulation what will happen if this loop runs again. If you were not able to visualize it even now, you can skip this part if you have got the concept. But see if for example this loop doesn't break here, this statement is not executed, then our command our processor would return to this line again. Okay, and it would run this whole loop again till we have this break statement executed. So until the user enters either H or C, the loop is executed again and again and again, and this message is also printed to the screen. And once the user enters a valid input, this statement break is executed and the whole loop just gets short-circuited from here. Fine. Okay. So now when we have got our value of this variable choice from this line, we can analyze it to make our game proceed. So if the choice is equal to C, so essentially the user wants to play against a computer, then is human versus human would obviously be false, because human is not playing against a human, and we declared this variable earlier if you remember. And again we use a while true loop as we would every time to take the input and to manage the wrong input, invalid input. So again it indicates the user to choose the AI level, then we use the getLine function, very similar to the previous ones, and try and catch block once again. Okay. So we use try and catch block everywhere where this function stoi comes, because this function might fail and give a runtime error straight away. So it's very essential to use a try and catch block here. Okay, we can't use a if else statement like we did here, because here it won't show a runtime error or something. Like here it could, because there was a while loop, but stoi just like would destroy our program as a whole if it does not run properly. If we pass wrong arguments to a function, it would definitely display an error. So to avoid that condition, we use a try and catch block here. Okay. So basically the input is again stored as a string, and we have to use this stoi function to convert it into an integer that can be processed easily. And if it's between 1 and 3, so basically if it's in these numbers, these three numbers 1, 2 and 3, then this while true would break. So this would exit the execution. And if it is not, then we have an empty catch here. So even if this throws an exception, there is nothing executed in the catch block. So this is only written here just for the caution, just for to maintain the caution that we don't get an exception here. Okay, but it does not run anything here. Again, it prints invalid move. If the loop does not break here, it prints an invalid move, and the user would enter again. The loop can run go on forever if the user does not enter a valid input, but I don't think anyone would be so foolish to do so. Okay, so now we move ahead. So first of all, we initialize everything. After we have taken the input from the user, we are now in a position to initialize every object in our class. Not every, but most of them. So first of all, player 1 is always stored as a human, and its shell state is black. And if is human versus human, just says that if this variable's value is not equal to 0, basically it's more than 0, then player 2 is stored as human 2, and shell state is white. Okay. So if this is not 0, it means that is human versus human is true, so the human is playing against a human, so player 2 must be stored as a human only. And the shell state of player 2 is obviously white, because we have already used the black state for player 1. And otherwise, if the game is played between a human and an AI, then obviously the other player's name is stored as computer with shell state of white. And if you remember, these were the other two arguments that we specified while writing this constructor in the player class. So these were the value of human and the level of AI. So you might wonder that we have used the same function in the previous line also and this one also, but we wrote just two arguments here and only but 4 here. So where were the other two, and why was there not a need to write them? So basically we declared these as default variables. We already gave them a default value to use, and if they are not written in a statement explicitly, then the compiler assumes by itself that it has to take the default values for these arguments. Here the arguments were true and the AI level was made 0, I think. So here, but AI level has to be generated as per the user demand, which user has entered, and human is obviously false because it is playing against because our player right now is a AI. So this character human is false, and AI level would be taken care of by this variable. We set AI level here, right? Okay. Now we again use this while true. We would use it again and again whenever we have to take any input from the user. Fine. First it prints the board. The print board function was from the board class, and this is an object from the board class only. So we can obviously use these functions. Now we store a variable named as score, and its data type is pair. I already explained how this data type is used, and it takes the value which is returned from this function board.countDis. This was the function again, if you remember, it returned the data type pair only, and we are storing up the value of a pair only here. You can refer to this function again if you have forgot where it was declared or whatever. And it first counts all the disks. So basically whenever a move is made or before a move, we print the score, the number of black and the white disks to the screen so that users can easily see the progress of the game. So here we in print the score black as score.first and score.second is the white score. Fine. Again, if I didn't mention this earlier, score.second and score.first are nothing but some statements which we write to access the variables from this pair. So pair essentially stores two integers as an ordered pair, not an unordered one. So if I store a comma b as a pair, it is always stored between these curly braces. So then score.first would give me a and score.second would give me b. So this is an ordered pair, like a comma b and b comma a are different. Okay, fine. Now let's move ahead. Vector move, current valid moves. So this is a vector. I already explained what a vector is, and it stored the containers, the small chunks of data it stores is of the data type move. The move was the structure containing the row and call objects. So first of all, why we declare this variable? It was to store all the valid moves which we have on the board right now for the current player. Okay, the current player by default was set as player 1. So the current player would be switched accordingly with the turns as we see further. This is an important operator, important symbol like this. So this is nothing but it just calls a function from this get symbol from the player class, and this is of the type player and it calls this function. Fine. So this is essentially a pointer, and to call this function on this like dereference pointer, we use this symbol. So it's nothing but it just gets the symbol either black or white through this statement. Okay, you need not worry about this right now, but just remember that it gives the symbol either black or white through this. Okay, so we have to like feed this function an argument either black or white, so it calculates the moves accordingly. So it can calculate valid moves for white or for black, and it does so after this argument is fed into it. Fine, and it stores all these moves, get valid moves, into this vector known as current valid moves. Okay, again we process this vector, and if this vector is empty, then we say that this player right now, current player, again this operator is used to get name from the player class only. This goes to the player class again, sees what the function definition was and runs this function. So the mechanism is quite simple, and it prints to the screen that the current player has no valid move right now. Okay, and it passes the turn. So if you remember during the rules, this is some theory of Othello. So during the rules I mentioned that if a player does not have any single valid move, the turn is passed. Basically our turn of the player is skipped, and now the turn goes to the next player. Okay, so we use this switch turn function. We will define it in our code later here only. Just be patient. So we'll see what this means, how it is implemented. But for now, just assume that switch turn is a function that helps us to switch the turns. So it basically changes the current player from player 1 to player 2, nothing else. And then it again evaluates if the second player has a valid move or not. And if it does not, if the get valid moves vector is empty here also, then we essentially got that there are no valid moves for this player, player 1 or player 2, whatever it is, and we have no valid moves for this player either. So we don't have any valid moves for any of the players, and this is where our game ends. So it prints the same message to the screen, and the break statement is executed again for this while true block to remain consistent. Fine. Okay. And this continue statement again, because this while true should keep running, the board should be printing again and again if the players have valid moves. For example, this break is not executed. Now you might think that there is no break executed here. So what I initially said, the statement I gave that we always need to use a break. A break should be executed at least one in a while loop. Is not that condition is not met here. So how do we maintain the consistency? How do we ensure that our program does not run out? So basically, if you visualize it properly, the break statement is executed at one point of time. Many times this continue statement is executed and this while true block runs again and again, but at some point of time when no player has any valid move, this break would be executed. And this continue is also very essential, because if a player has a valid move, and the switch turn statement is executed again, switch turn is executed and whatever. So basically after printing the board, after taking the input and after computer being able to make the move, this loop should run again. So you should have noticed during the demonstration that the board was printed every time a move was made, and this board.printBoard function was executed every time. So it was possible only through this while true loop. So till the game ends, till this break statement is not executed, the board would be printed again and again after each move. Fine. Okay, let's go ahead. Again, this is something which indicates whose turn it is and these things. So let's investigate what this block of code says. First of all, we are using these symbols again and again, so I don't think there's a need to explain them again and again. You already know what this means, and this function is also familiar. These functions, these are from player class. Okay, so it first tells after each move that it's turn of this player or this player, and it also mentions the cell state. Okay, this is nothing but an output statement, so it's quite easy to analyze. There's no new logic or code, so nothing much to explain here. But here we see if the current player is human. Get is human was a function that returned if get is human was C. What that was? See, basically it was a function that returned the value if the if player was human or not. So if we check if the current player is human, then from this we get player move. Again, these functions are executed. These functions are executed. Get player move, and this function. Now we get the player move, and again it could be of type -2, -2 or -1, -1 or a valid move. So row between 0 to 7 and a call between 0 to 7. Okay. So we need to analyze the value of this function, the value which is returned from this function for our program to proceed. And first of all, if move.row is -2, we get to know that the user has asked for a hint. Then we execute the statements whenever what should be executed whenever a user asks for a hint. So calculating best possible move is nothing but something which improves the user interface possibly, I think. Then move.best move. Again, the logic behind this is we find the best move. I explained these functions earlier, so I hope you remember them well. So it gets the best move by these arguments or functions. These are again very easy. Fine, their depth has been taken as 8 here. Actually, initially I planned to take the depth 4 here to give a computer advantage, not an unfair, it would not, like computer should be having some advantage if it's giving hints to the user. So this depth should be 4 only, but I kept it 8 to make it a fair playing ground between, but like if the user asks for a hint from the computer, so it should give the hint as thoroughly and the best one as it could. So we have kept the depth here 8 here also, but there's something which we lose while doing this. That is our time, because as we increase the depth, and I told this earlier also, as we increase the depth, our decision tree gets bigger exponentially, and with the length of the decision tree, the time to calculate the best move also becomes very large sometimes. But here it does not run beyond 12 or 15 seconds, so it does not matter much, because a human takes on an average 30 seconds to a minute to make a move. Okay, so this shouldn't be very troublesome. However, it does slow our program. Again, it just mentions what the hint is through this statement, and it continues. Fine. So this should be totally fine. Okay. Now let's move ahead. If if this function returns true, this board.make move, this is returned true. Basically, if this is a valid move, this make move function was defined so as to return if the move is valid or not. Again, there are many functions here, so you can go to them again if you want to, and refer if the syntax is correct or not. You will get the logic correctly only if you go back to these functions and see how they are defined. But if you remember as I do, then this function returned nothing but if the move was valid or not. Fine. So we see if the move is valid or not, and if it is valid, then we switch the turn. We would be coming to the definition of this function, don't worry. We switch the turn, else we print an invalid move. Okay. So this was something you might think like we already handled the case of invalid moves before, so we are doing it again and again. No, it's not like that, because we just handled the cases with like something like not matching with our format, like small a and capital A character and a number. That format we handled. But what if user enters something like 8, 9? We didn't do anything numerical there, if you remember in the try and catch blocks. So this won't be eliminated. And even if there's something like user enters something between 0 to 7 only, but still the move is invalid. What if this disk is already occupied? So there are many possibilities of invalid moves which we haven't encountered right now, and this board.makeMove functions takes them into account, and this invalid move is printed if the move is invalid. Fine. Okay, let's move ahead. Okay, one thing if I didn't mention was the essence of this continue statement. So basically this was if a user has asked for a hint. This block should not be executed. Like it's not needed at all. Because if user has asked for a hint, this shouldn't be executed, and this is what this continue statement does. It basically switches the command prompt to the start of this function. So whenever we have a break function, our line of execution goes to end of the function, and whenever we have this continue function, essentially the line of control goes here to the start of the function. Fine. So it does not execute this block, and it goes here to execute further statements or to run the loop again. Okay. So uh, okay, if the user has otherwise no, sorry, if it's not user's turn, the human's turn, and if it's computer's turn, then we use this to enhance the user interface again. And move computer move, we have declared a variable computer move with this struct move int scale equals to get skill level. So this is the AI level and nothing else, and we have to make moves according to various skill levels. Fine. So the move would be different if user has chosen an easy AI, and it would be obviously very different if the user has chosen an hard AI. So if scale equals 1, if scale is 1, then the move are randomly selected. Okay, so it selects any random move, it generates all the valid moves and selects any random move from this. Okay, let me explain how this works. Okay, first of all, this is a statement from cstdlib library. So, fine. Now, basically how this works is, it gets the size of the valid moves. For example, we have 4 valid moves right now, and it selects any one of them. So the index could be either 1, 0, 1, 2, or 3, and it selects any one of these. Okay, now you might think that this everything inside this square braces must assume a value of 0, 1, 2, and 3 with equal probability, right? So how this is ensured? So basically rand percent current valid moves. So rand just generates any random real number, just any random, not real but natural number, obviously, any random natural number, and it takes the this percentage, this the remainder modular operator. This takes the remainder that is left after we divide rand by this thing current valid moves dot size. So if n is the size of current valid moves, the rand percent this thing has the possibilities from 0 to n minus 1, because the remainder can't be n. If the remainder is n, if the remainder is n, then it is the same case as the 0. So we don't need to think about that. So our cases is just 0 to n minus 1, and they have an equal probability, obviously, because random takes any random natural number. Fine. So current valid move always assumes a valid index from 0 to n minus 1 as its length was n. And it is obviously very random because all have equal probability, as I explained. Okay, so else if scale level equals 2, you got it right? Okay, so else if scale level equals 2, then int best flips is minus 1. Okay, what this does is the scale level was the greedy player. So the greedy algorithm is nothing, but it just makes the best possible move right now according to the parity of the disk. Okay, so it basically checks all the moves that it can do right now and how many disks each of them would flip, and it assigns this value of best flips to that move which has the maximum number of flips, and the computer move is assigned that value only with the maximum number of flips. Fine. The logic should be clear. Now coming to the implementation part. Again, for this is a for each loop. Okay. And current valid moves we check for each m. In current valid moves auto, I already explained const auto. Const is nothing. You can leave it right now. Basically it just indicates that the variable m is not changed. Okay. So const auto just ensures that we don't have to write move. We could write return move here instead of auto. It won't change much. So fine. For each m in current valid moves, this is m is a variable of this data type, const move and fine. Okay. So for each valid each data in m in this current valid moves vector, it would calculate the number of flips, and if flips is more than this best flips, computer moves would be made m and best flips would be equal to flips. Fine. So this is quite easy. It's just like how we find the maximum element in an array and nothing else. Okay. Now let's move ahead. Basically, one more thing I would like to mention here, you might think that greedy algorithm is always the best, though you might have cleared the concept from that positional weights and the mobility score table. However, you might still think that greedy is always the best, but it is not, because here, as my slide states, it lacks the long-term planning and it can't see if the disks right now are more in number. Even then the opponent could place one disk and flip the whole board. Okay, now let's move. Else we have tested it for skill level 1 and 2. Now only skill level 3 is remaining, and that's the hard AI part. So else the depth is set as 8 and the algorithm of minimax and alpha beta pruning is executed through this line as we saw earlier, and the computer move is decided according to that only. Okay, fine. Okay, so board.makeMove, this is now when we have determined what this computer move is, we execute that move to our board. Okay, so we have already seen the implementation of this function, and you can check the arguments also. Okay, and if it was computer move right now, then it prints computer plays the move which it has played right now, for the clarity of user, so that he does not have to locate on the board where the disk was placed and all these things. And again, obviously it switches the turn, so the turn now goes to the human player. Okay, obviously after each move it has to print this board. Fine. Okay, if now the game has ended, it prints the board again and it stores the final score as this board dot count is. Why are we doing it again? Because we've already mentioned these things in the loop, because the loop wouldn't run till here. As we find no valid moves, the loop ends and it does nothing else, but we need to indicate that the game has ended. So we first print the board just to print the final state, and we store something like final score with the data type pair again as board.count is. Okay, and again we print the final result of the game through these statements, and you can obviously see how these are done. This is not very significant part of our project, so let's skim through this fast. Fine, all these things must be fine. Now we check who has won through this. Okay, this is fine. Then if the discount of pair 1 is more, then pair 1 wins. else player 2 wins, or if none wins, then it's obviously a draw. Fine. So this is the switch turn function. I think it's getting cut here. I'm sorry for that, but it's nothing like here it is written void and switch turn. Okay, void switch turn. So I'm sorry for the trouble. It's getting cut here. I don't know why, but it's void switch turn. Okay. So I already mentioned the logic behind this player. It just checks if the current player is player 1, and if it is player 1, it makes the value of current player as the value of address of player 2, and otherwise it is of player 1. This is the use of ternary operator once again, and I hope you are very familiar with it right now. So if current player equals and player 1. So basically this first checks if the current player stores the value of address of player 1 right now. And if this is the case, then the value of current player is changed to the address of player 2. And if this is false, if this is false, then current player obviously stores the value of address of player 2. And if it is so, then the value is changed to the address of player 1. Fine, this is very simple. Okay. Now this is the last part of our code, and as I mentioned earlier, now you see with all the applied object-oriented techniques how significant the main function is. It is just reduced to merely 5 lines of code and there is nothing else. Okay, so this function is from CTime library here. So this is nothing but it just ensures that the user doesn't repeat its move. Fine. So it randoms the move according to the time. Okay. So you can read from here also. It ensures that easy AI, which uses the rand function, produces different sequence of move each time the program runs, making the game more varied. So the easy function was very easy, like it was really easy. It just chose some random move, but still to make it non-monotonous, we use this srand so that it moves a different move every time we play the game. Okay. Now we declare an object game from the class game with these specifiers. So this is the use of a constructor essentially for the first time. Here this is the initialization list and nothing else. If you go back to the constructor and see, these were the arguments that we mentioned in the initialization list. Okay. And as I earlier mentioned, while I stated the definition of the start function, this is the only function which we would need to call inside our main. And it is the same thing. We call this function and whole of our project comes into existence only after the call of this function. And all the logic of main function, everything is stored in this line. Fine. And this is the conventional return 0 statement, which indicates that our program has run successfully. Before we wrap things up, I want to give a special shout out to a few key individuals and resources that were absolutely vital in bringing up this Othello project to life. Firstly, a huge thank you to Dr. Goswami, my professor, for his incredible guidance and support throughout this entire process, and for teaching me this beautiful language of C++. Next, I would want to thank Professor Stuart J. Russell and Peter Norvig. Their comprehensive textbook on AI was an indispensable resource, providing the theoretical backbone for our AI designs. And finally, a big thank you to Professor Sir Dave Churchill, whose insightful lectures were a constant source of inspiration and practical knowledge for me. Also, last but not the least, I would like to thank every viewer who has watched this video. A massive thank you to you. I really appreciate your patience and hope you found this deep dive into Othello and its AI both informative and engaging. And for sure, if you have any questions, thoughts, suggestions, or future enhancements, Or if you think I missed anything, please don't hesitate to leave a comment down below. I love hearing from you all. Thanks again for watching.